Okay, well, good morning again. This happens also with instruments. You have an instrument, sometimes the computer's not working right or something's not going on in the machine. So you have glitches that you have to work out and fix. Okay, so thank you very much for taking care of that problem this morning. Now, in XPS, what we're often doing is trying to understand chemistry. So we identify the elements present by what we take in a survey scan, which is taken at a high pass energy in the analyzer to detect the elements. Then once we detect the elements, what we'd like to do is learn as much as possible about the chemistry. And the chemical shift when you change the environment of an atom is very, very useful. But this is an area where a lot of errors are made because people fit their spectrum with too many peaks. So you have to have a good reason to put so many peaks in to do a fit. And this is a very simple case. This is a polymer. And this is not my data. This is from that database I mentioned, that CD. And it shows you that this particular carbon spectrum, the carbon 1s spectrum, has at least 4 peaks. And what you do is you fit a component to each of these peaks. So the line sheet you use for the fitting is also very important. In this case, you can see the background here has these little stretched S's that I mentioned yesterday about the Shirley background. And the Shirley background is what I typically use for curve fitting. So you're fitting the peaks above a background. And you can also plot residuals to see what the residual is. The residual is the difference between the spectrum you acquire and the peaks that you're fitting. So we can see here 4 peaks, approximately equal areas as well. And that relates to this particular polymer. This is exactly what you would expect. It's from the polymer handbook. These are spectra of known polymers, and this is what you would expect to get. In many cases, you don't know what you're going to have. So you have to use the knowledge you gain from the spectrum to ascertain what the chemistry is. So this is an example of some work that I did. This is a simple spectra also of silver. And it shows you also curve fit data here. So this is silver. And the background is obtained over this region here that's indicated in the blue color. And what I used here is Shirley background again, and the endpoints are subjective. You have to take a guess as to where the endpoints would be on the data, where the peaks are. So if I asked each of you to do a curve fit on this particular spectrum, I might get slightly different results on the endpoints that you choose. But again, you can see this stretched S shape, okay, background, the Shirley background. So I have a doublet. And remember for silver, these are the 3D peaks. It's a doublet. And the ratio of the areas of the peak should be 2 to 3. So that's something that we know. And also from a handbook, we know the separation of these 2 peaks as well. So that's information you can also put in to your curve fit to improve the fit. So we know the ratios of the areas should be 2 to 3, and we also know the energy separation. But I don't put constraints in unless I need them. I like to do a fit and try to do it and get the right answers, get the right areas, get the right energy differences between the peaks. And if you get those answers, you know what you've done is reliable. So here I'm using a line shape. I mentioned yesterday about line shapes being Gaussian and Lorentzian. Now, do you remember? The analyzer gives you a Gaussian shape. It's a Gaussian broadening function. And the natural shapes of the lines are Lorentzian. So when you take data, the line shape is going to be a combination of a Gaussian and Lorentzian line shape, depending upon the resolution of your spectrometer. The better the resolution, the more Lorentzian the line shape will be. And this is a problem a lot of people don't realize in doing curve fitting. They always use the same line shapes in curve fitting and don't adjust it for different resolutions. So I want to show you that kind of issue you have. So on the left-hand side here is a fit of a Gaussian and Lorentzian, with 30% being Lorentzian. So L is Lorentzian, 30%. That's what we have. So we're going to have 70% Gaussian, 30% Lorentzian. This is a line shape that's commonly used in almost all XPS instruments. Yeah, you provide you with a Gaussian Lorentzian line shape where you can change how much of each one you have. So in this particular case, I use 30% Lorentzian and try to fit these two peaks with that particular line shape. And if you look at the data in color here, you can see that the peak fit is excellent. It's a little bit of a difference here in the spectrum between what the raw data, which is in the red here, and the two component peaks. So it's not perfect, but it's really good. And the reason I say it's really good is what you're doing is you're looking at the fit with the peak maximum. In other words, the peak that we're fitting is aligning up very well with the data maximum. So good you can't really distinguish them. And also you're looking at the shoulders here. The shoulders also fit very well with the data. Now, if I use a different line shape, on the right-hand side, I'm using 90% Lorentzian. So I'm going to have more tailing at the bottom of the peaks. And now you can see that the peaks that I'm fitting do not line up as well with the data. So the raw data is the one in red here. And the curve fit data, when I optimize the curve fit mathematically, that's done by the computer. You ask it to optimize the fit. Now you can see that with this line shape, the peak maximum is above my data point. And you can also see the same thing for this particular part of the spectrum. My peak shape that I'm using gives me too high an intensity for each peak. But also you'll notice, again, the raw data here is in the red, this one. And the line shapes I'm fitting are more Lorentzian. So you have this bigger tailing over here, you see? And the same over here, you can see that as well. So that is not an appropriate line shape for that particular spectrum. So 30% Lorentzian gives me an excellent fit for that particular spectrum. Now, what if I change the resolution of the analyzer? Okay. So if I change the resolution of the analyzer to improve it, I'm going to have a line shape that's going to be more Lorentzian. And that's shown here. So now the silver spectrum is sharper. Also, you can see these loss features. And what I'm interested in doing is fitting just these two main peaks. I'm not worried about fitting these loss peaks here, just the main peak. And when I do that with the 30% Lorentzian, it's hard to see here, but the peaks don't fit well at the maximum. But also down here, the peaks that I'm using for fitting don't fit well either. You see that? This is the fit here in the purple color for this one, and in this aquamarine here for the smaller peak. So these peaks here are too Gaussian. I need more Lorentzian character to give me more broadening at the base. So now when I use 90% Lorentzian, I get an excellent fit for the two peaks. I get excellent fit for the peak maxima, and I also get an excellent fit to the base here of each of these peaks. And remember, these two features here are associated with energy loss features in the spectrum. I'm not concerned about those right now. I'm just concerned about making a fit to the two main peaks. So you can see how you must use different line shapes when you have different resolutions. And these peaks are quite symmetrical. In many cases, you will not have symmetrical peaks. You'll have broadening occurring, and that makes another difference to a fit. A common error that people make in doing curve fitting, for example, this is the default line shape in one of the data processing packages, 30% Lorentzian. So if you just leave it as the default, I've seen people add extra peaks to get good fits. So people will add another peak here to allow for this discrepancy, a peak here, and similarly over here. Because the more peaks you put in, the better the fit's going to be. But you only want to put in the relevant peaks that you really need. And people will put extra peaks in and then claim they have different chemistries. They have other components present, but they don't. They're using an incorrect line shape. So by changing the line shape to this 90% Lorentzian, I get an excellent fit. And the other thing I mentioned was, then I also check the relative areas of these two components and check and see if they are 2 to 3, and they are. So I know I have a reliable fit as well. So that's a very simple case of curve fitting on silver, where the peaks are quite symmetrical. But this is an interesting case. This is a spectrum of rhodium, 3D doublets. And this was sent to me by somebody in the United Kingdom. And they told me that in this particular case, they got excellent fitting, but they could not fit the spectrum from the pure rhodium metal. And they asked for help. So what I did was, they sent me the data. So I put it into a data processing package that I normally use for all my curve fitting, which is called CASA XPS. Some of you that do XPS may be using CASA XPS. It's a fantastic program for doing curve fitting of in XPS and other areas as well. But you know what? The person that sent me the data said he had an excellent fit. Well, yes, the sum of the 6 component peaks here fits the measured spectrum very well. So you can see the raw data here is in red. And these are the 6 peaks that were fit. 1, 2, 3, 4, 5, and 6. So the sum of all those individual components fits the data exactly. Beautiful fit. But you know, even though he told me he had no trouble fitting that one, he's wrong. It's completely wrong. Why is it wrong? It's wrong for some different reasons. The most important reason it's wrong is that the ratios of the areas of the peaks are not correct. So again, in the rhodium doublet, the ratios of the areas of the 2 peaks should be 2 to 3. So he's using 6 peaks. So he's thinking that he has 3 different chemistries, and each of those gives you a doublet. That's why he's using 6 peaks. But no constraints were put on the data. So this peak here in purple, see this one here in purple, is basically corresponding to this one over here in this teal aquamarine color. Well, if you look at these 2 peaks, the energy separation of these 2 peaks is correct pretty well for rhodium. But look at the areas. The areas of this peak and this peak are not 2 to 3. This peak has an area that is as big as or bigger than this area. So that's wrong. The ratio should be 2 to 3. Let's look at the other doublets. This peak corresponds to this one. Well, the ratios again are wrong. This peak here is not the ratio of 2 to 3 with this blue one. This peak is too small. And the other doublet, this one and this one, again, this area, in this case, is bigger than this area, and it's not 2 to 3. So by not constraining the intensities of a doublet, you do get a good fit, but it's incorrect. So what the person should do is to constrain the ratios of the areas of those doublets to 2 to 3 so that you do get correct physics in the fitting. Now, you constrain that. You can also constrain the energy separation of the doublet. But also you can constrain the full width of half maximum of a peak. And the full width of half maximum, if you just take this peak here, for example, full width of half maximum is this full width of a peak at half its height above the background. And that's the full width at half maximum of a peak. Now, the full width at half maximum of a peak in a doublet does not have to be the same. In some materials, it's very close. Other materials, it's not. It's very different. For example, titanium. The titanium 2-piece spectrum, the full width of half maximum of the 2 peaks in the doublet are different. They're quite different. But in many cases, they're very similar. And this comes by looking at reference spectra and also from experience as to what you can constrain and not constrain. So I refit this data by constraining the energy separation and the ratios of the areas. And the fit with the 3 components is good, but not perfect. This one here you can say is perfect because you're letting all these variables take care of these, the difference between the raw data in red and the fit data, summing them up. So the components in this case are incorrect. And this is what I'm getting at when I was talking about a lot of publications, about the further publications in XPS, particularly on curve fitting, are incorrect. Because the people doing the curve fitting do not understand that you must constrain certain things and have good physics behind what you're trying to fit. So this one here that he said he could fit very well was incorrect. And I emailed him back and said, yes, it's not good. It's incorrect, and told him why. And I sent him what I did as a good fit. Now, of course, there might be other components present also in the rhodium. There might be more than 3 components, but 3 components gave a fairly good fit, but not perfect. And the line shape he wanted to fit, he could not do. And that's this one. And if you use the default line shape, so you go back here, see he was using the default line shape, which is 30% Lorentzian. That's the default line shape in the software. So if I take the other spectrum he sent me, this is rhodium metal. It's a 3D doublet. and he could not make a good fit. So he was using the default line shape, 30% Lorentzian, and Shirley background, 2 peaks. And when you create these 2 Gaussian Lorentzian components and fit them to minimize the residuals, this is what you get. The raw data is in red, and you can see the peak maximum in the component peak does not come up to the maximum in the data. And that applies to both of these peaks. You'll notice down here on this side, this low binding energy side of the peak, the fit is reasonable. But over here, on this high binding energy side, okay, the raw data is in red, and the fit is not good. This is the fit here, again, in this bluish color. And in between here, also, the data is not fit at all well. And that's why he said he couldn't fit it, because he was using this Gaussian Lorentzian 30% line shape. So this is a case of a metal where the peaks are asymmetrical. And unfortunately, a lot of people, to get a better fit, will say, oh, I have some other chemistry present. I have some components here at higher binding energy due to some particular compound of rhodium. Well, in the spectrum, there's no other elements present. It's pure rhodium metal. So you know there's no other components. So he was trying to add more peaks. And as I mentioned, the more peaks you add, the better the fit. But there's no physical reason to do that because there are only 2 peaks. And what you have to do is change the line shape. You have to use an asymmetrical line shape. You can't use asymmetrical Gaussian Lorentzian line shape. So what I did was use one of the asymmetrical line shapes that's available in the CASA XPS for curve fitting. This is an asymmetrical line shape, which is based on a Lorentzian function with Gaussian broadening. And I can change the amount of Lorentzian character on each side of the peak. On this low binding energy side and the high binding energy side, I can change those. And look at what I get here now with this particular line shape. This is an asymmetrical Lorentzian. And these are the 4 parameters that you can adjust for this asymmetrical line shape. And you can see now that the line shape that I'm using, this one, gives a beautiful fit. The peak maximum in the components match essentially exactly the data, the raw data. And look at the, on the right-hand side of this peak, matches beautifully the line shape. And on this particular component on this side also matches the data beautifully. And that's because the peak is asymmetrical. So these 2 peaks that I put in that have this particular line shape match the data beautifully. You can see a small discrepancy here between the raw data, okay, and some of my 2 component peaks. But just using this line shape, it turns out the ratios of the areas are also correct. It's 2 to 3. So this is something that's very important to understand in curve fitting. You must think about the physics, what is present and what kind of line shape you use. Just don't add more component peaks to get a good fit. Otherwise, you're going to have an incorrect result. And in this case, it's easy to know you don't have extra chemistries because it's pure rhodium. So there's only 2 peaks, and you have to select a line shape to get a fit. So this is an example. So, and that's why you get so many errors in the published literature. For example, this person could have published this work and said that he had these different components and so forth. And then people think this is correct. See, but it's not. So I was very happy that he sent it to me so I could point out to him that it was not correct. And it was from somebody who took a class from me some years beforehand and forgot about some of the things to do. So it's easy to forget, okay, about different things that you have to include in making good curve fits. Now, just to give you a few examples of some bad curve fitting. There are many cases of bad curve fitting in the literature. And in prestigious journals, as I mentioned. So if I could just start off and show you one up here. This is a spectrum here of oxygen. Oxygen 1s XPS spectrum here of this particular compound of gadolinium and zirconium oxide. And they say it can be fitted by two Gaussian functional curves indicating the different anion migration mechanism from that in this particular compound. Well, see, they want to find something in the spectrum to confirm their hypothesis that they believe what's happening. And they think that these components here explain that. Well, this is completely wrong. First of all, the data is very noisy. This means, to me, that they took the data with too many data points. I do not need all these data points to get this line shape. I'm much better off using fewer data points and taking more scans to get better signal to noise. So that's the first mistake that they made in taking this data. Okay, so they should have used fewer data points. Well, you can smooth the data. And when you smooth the data, I don't like to smooth data. And I'll only smooth it in cases where somebody's made a mistake like this of taking too many data points. So when you have too many data points, you can smooth the data. But I normally never smooth data. I normally fit the raw data. And the mistake is, can you see the mistake in this? These two components. Well, this component may be real here, and there's a little residual here based on, you know, the fit of this peak compared to the raw data, even though it's very noisy. And there may be a component here, but it definitely is not this shape. You see, the 4½ maximum of this peak here is approximately 1 electron volt, or 1.5 electron volts. Whereas the 4½ maximum of this peak here, you see across here, is like 4 electron volts. And this peak is too sharp. So it doesn't have a realistic width to it. So it's not a good fit. It's incorrect. And this is in Phys Rev Letters, Physical Review Letters, very prestigious journal. Well, here's another example. And this is published in a Nature journal, Nature Communications. So they're looking at these peaks here of sulfur and comparing these two. I'm just putting in two of the peaks here, D and G from their paper, to show you some of the errors. And they're using these spectra here to claim all kinds of differences in the reactions and chemistries between these two samples. Well, if you look at the data, you can see many errors in here. And the simple one to look at is this peak here that they've labeled in red as SO3 -2, this one. And in this spectrum, they've also put in SO3 -2. But if you compare these two, you'll notice this one here has a very sharp peak, a very small 4½ maximum compared to this one. So that's an error that you can see. If you have that chemistry present, you're going to have the same line shape. So that's one of the mistakes they made. Also, over here, they've got some peaks labeled different ways. This peak over here, again, is very sharp. And this is not compatible with all the other peaks. You're not going to have sharp peaks like that. So they claim they have all these different chemistries and have a good fit, but didn't constrain the peak widths, for example, between the two spectra to make a good comparison. All they wanted to do was get good fits. So their interpretation of these sulfur spectra are incorrect. There are some other errors in here as well, but those are some of the obvious ones that published in Nature. Now, here's another example down here in the bottom left, iron spectrum. Well, iron has a doublet, the 2p's a doublet, and it can have also complicated spectra. But look what these people did in fitting their data. They've got 2, 4, 6, 7 peaks in here to fit their iron spectrum. Well, with a noisy spectrum like that, it's hard to make any fit to the data. Again, they probably used too many data points, but look what they've done again. They just added extra peaks to get a good fit to the data that they think would be reasonable amongst the noise. But put no constraints on and put all these extra components in, and there's no way that they could claim they have this peak here, for example, as well as this main peak. So putting all these extra peaks in with no constraints gives you what might be a good fit to noisy data, but you don't know what the real spectrum looks like to make a fit. So again, it's not a good spectrum. They should have taken their data for a longer time or used also fewer data points before they want to fit the data. And also the peaks may be quite asymmetrical, and they're using symmetrical peaks in fitting the data. So you have to have an understanding of what the iron doublet looks like, the 2p doublet looks like, fit it, some compounds of iron. So it's nice to have a database of different chemistries, for example, of iron, because in some cases the peaks may be more symmetrical than others. And also you might have these so-called shake-up effects and so forth in your spectrum, which makes it more complicated to make a fit. So these are a couple of examples of bad curve fitting. Here's an example of XPS where you might think that the technique is not very useful. And these are spectra that I took from the XPS of polymers database to illustrate polyethylene and polypropylene. And the carbon 1s peaks here in these spectra, they're offset here for clarity, are extremely similar. Okay, so these are very simple polymers. So the carbon 1sp does not distinguish between these two polymers. So if you're working on polymers, one of the very useful parts of the spectrum to examine is the valence band region. And over here is the valence band of these two different polymers. These are pure polymers. And over here, you can also see some similarities in where there are peaks, but also you can see in this particular one here in the polyethylene, you have this other peak here as well. So these particular studies of the valence band show you the differences in the spectra between these two polymers. So if you're trying to distinguish these two polymers, you might have a blend or something like that. You look at the valence band, and that's something that a lot of people also ignore, but it's also useful. And that's one of the reasons that people also use the technique that I mentioned about ultraviolet photoelectron spectroscopy, which is designed to really look at the valence band. It gives you good resolution, good signal. With X-rays, the signal intensity is much lower than with ultraviolet rays. So this gives you a good example of the case of the polymer. Now, in some software packages in CASA XPS and also in Avantage, which is a software package that Thermo uses in their instruments, it's possible to use these line shapes as the line shapes for fitting your data. So if you had a mixture of these two polymers, you can use this line shape here in green as one component and the line shape here in red as another component, and fit the valence band of your mixture by using these line shapes. So you don't have to use an artificial line shape. You don't have to use a Gaussian-Lorentzian line shape, or you don't have to use an asymmetrical line shape like I showed you. You can actually use reference spectra as the line shapes in fitting your data. So that's another useful aspect in the software, is that you can use real data as the line shapes to get really good fits of your spectra. Now, depth profiling, I talked about this already in Auger spectroscopy. They determine the composition with depth from the surface. There are non-destructive methods. Now, in XPS, we have angular studies, AR-XPS, angle resolve XPS, which can be also very useful for looking at the compositions near the surface. Remember, we're looking at a certain analysis depth. 3 lambda cosine the angle theta is what we're looking at. And by changing the angle of emission, the theta, we can change the depth of analysis. So by doing an angular study, we can see the near surface composition variation with depth. So angle resolve studies can be very useful. As a matter of fact, Thermo made an instrument designed just to do angle resolved XPS on a sample, particularly for the semiconductor industry. Another method is also to look at the inelastic losses associated with the peak. I showed you that the low to higher binding energies, lower kinetic energies of a peak, we have a background. And if an element's buried, the background will be higher in relation to the peak area, because the signal is coming from deeper down in the material if it's buried, and therefore the electrons are losing energy as they come towards the surface and go into our spectrometer. So the background will be higher than what you would get from the pure element. Destructive methods, sputtering is what we normally use, and there might be some mechanical methods, for example, chemical etching or things like that, to remove certain layers if they're quite thick. And sputtering is what we normally use, typically an inert gas of argon, to do a depth profile. So I'm just going to start off and show you a couple of examples of angle resolved XPS. This is a principle of angle resolved XPS. This is a sample. Remember, I told you that the depth of analysis, 95% of the signal comes from 3 times the inelastic mean free path times the cosine, okay, of the angle of emission. So in this particular case, in this slide here, that I borrowed from physical electronics, they've got 3 times L, and L is like the inelastic mean free path, but they're using sometimes a different number called electron attenuation length. So some people will use inelastic mean free path, other people use electron attenuation length. Now in this equation, they're using sine of alpha, this one. And this is not the angle of emission. This would be angle of emission of 0, and this angle's 90. So this is called a takeoff angle. So in angle resolved XPS, you'll often see people refer to a takeoff angle. So alpha is the takeoff angle, and it's equal to 90 degrees minus the angle of emission. So if you're using takeoff angle, it's the angle in relation to the surface plane between your analyzer and the surface plane. Then you would use sine of alpha. Angle of emission, you would use cosine. Now, so the depth of analysis, 95% of the signal is coming from this depth, D. Now, when you tilt the sample, for example, which is a common way for doing angle resolved XPS, in the material, the distance here in the direction of the analyzer is still the same. So the electrons are coming out now through the same length here in this direction in relation to the analyzer, the same length here. But in relation to the surface normal, D here is much smaller. So by changing this angle, this takeoff angle now is small, you've decreased the depth of analysis. So you take spectra at different angles of emission, and from that data, you determine the composition near the surface. Just a couple of examples. On the left-hand side, we have this is carbon spectrum, carbon-carbon bond, and then carbon with fluorine. And these are two different angles of emission. And you compare these two spectra. This spectrum here in red represents a bulk measurement. So this is going to be the case on the left-hand side here when you want the maximum depth of analysis into the sample. But when you tilt it, you're going to get a signal from more near the surface. And that's going to give you this spectrum here in green. So compared to the carbon-carbon, you can see that the fluorocarbons increase intensity relative to these. So you know the fluorine carbon is present more at the surface than below the surface. Because if it's uniform and I tilt the sample, I'm going to get the same spectrum. Okay, I'm not going to get a change in the relative intensities. So angle resolved XPS is a non-destructive way to learn about the near surface composition of the material. And on the right-hand side here is the case for metal, niobium. The same kind of thing. They're doing angle resolve here. Okay, this niobium metal, different oxides. In this particular case, these are oxygen spectra. And they're using a bulk sensitive angle to look as deep as possible into the sample and using a surface sensitive angle to see if they're different. And the spectra are very different. So from this, you can interpret which components, which chemistries are near the surface. So it's not a homogeneous material. There's a variation in composition chemistry near the surface. But the angle resolve work is non-destructive. You're not changing your sample. You're learning about the near surface chemistry and how it changes with depth by these kinds of measurements. Now, when you do one of these angle resolve measurements, there's also, you do calculations based on the inelastic mean free path, intensities and so forth to ascertain the depth information. But if you have a simple case, for example, of a silicon oxide layer on silicon, when you tilt the sample, you'll also get a change in the signal intensities of the oxide component versus the elemental component. So angle resolved XPS is very useful for looking at the thicknesses of oxides, for example. And when you have a chemical shift of silicon, the kinetic energy of the peaks is still basically the same, so you don't have to correct for that. But one of my colleagues, Peter Kumson, who also did a lot of work on electrons traveling in materials, came up with this particular plot, and he calls this a thickogram. And I find that many people like to use this, but very few people know about it unless they've taken my course. So in his publication, he also has one of these without this particular line drawn on here. So what you use to determine the thickness of a film using a thickogram is really easy. So IO is the intensity of the peak in the overlay. So this would be the chemically shifted oxide peak of silicon, for example, divided by sensitivity factor. And then the substrate intensity divided by its sensitivity factor. And this ratio of the ratios okay? There's a certain number. And you go up this vertical line here and get the point A, which equals this particular term here. So this is point A, this value here on this vertical line. And then over here on this particular plot, you do the same thing. You select the curved line here that has the same value as this one. So you can see this point A is between 2 and 3. So you come over here between 2 and 3 and come down where that line would be. And you come down here to this point B. And point B is the ratios of the kinetic energy of the electrons coming out of the overlayer peak divided by their substrate energy. Now, if it's silicon, for example, oxide on silicon, it's going to be essentially 1 because the kinetic energies are very similar from those two peaks. And then it would be on this particular line. But this example shows you different materials, okay, where it's not the same kinetic energy for the electrons coming out of the overlayer compared to the substrate. So these vertical lines represent the ratios of the kinetic energies, not the binding energies, kinetic energies of those peaks from those two elements. In this case, that ratio is here, a little greater than 0.8. So you get this point B then, you join these A and B with a straight line, and where it crosses this particular curve at point C, here you can see it's crossing at 1.4. This 1.4 value is equal to the thickness of the film divided by inelastic mean free path of the electrons in the overlayer times cosine of the angle of emission. So this is a graphical way to calculate out the thickness of a film. Very nice way to do it using this thicogram. So something to be aware of. But normally in XPS, we're using a sputter depth profile. And we're going to remove material and look at the new surface. So surface layers are removed by sputtering with inert gas ions. After you sputter, you create a new surface, and then you go and look at the composition of that new surface, and you do this sequentially. You will sputter, create a new surface, analyze it, sputter, create a new surface, okay, analyze it, and so forth. And you repeat this to get the composition at a series of depths in your sample. Same slide as I showed yesterday, basically, except now we're using X-rays. And the diameter of the X-ray beam is going to be bigger than the electron beam. So you're going to have to raster it, again, the ion beam, but typically now over a larger area because the X-ray beam is much larger than the electron beam that we would have used in Auger spectroscopy. So you must analyze the composition in a flat bottom crater. You don't want any signal coming from the walls because those represent different depths. Some instruments also can look at the small areas by using the input properties of the input lens to narrow down the area of analysis. So in sputter depth profile in XPS, you must know the area of your analysis, how big that is, whether it's determined by the X-ray beam size or by your spectrometer. And make sure that you raster the ion beam over an area that is big enough to make a flat bottom crater. Yeah, the question was, or the comment was, that when you're using, for example, argon as an ion beam to create this crater, what is the effect of the argon on the spectrum? Well, argon's an inert gas, so it's not going to react with your sample, but in many cases, you'll see argon in your spectrum because it's implanted into the material. So that's one aspect. But you know it came from the beam. Now, if you have a sample that has argon in it, for some reason, and you're interested in argon, you'll use, for example, a xenon beam, a different gas, do your profiling. So I've had some cases where people were interested in argon in some materials because they grew them in argon gas. So then I used the xenon beam. So if I measured argon, I knew it came from the growth. It was in the growth process and incorporated in the film and not from my beam. So yes, you'll see argon in many cases from the implant, from the ion beam. And the higher the beam energy you use, the more of the implant you're going to have to a greater depth. So yes, it is an issue, but normally it's not going to be a problem because you know it's going to happen, and unless you're studying argon. Okay, thank you. Okay, so we do it sequentially. We raster the ion beam, we stop the rastering, we measure the photoelectrons coming off at depth, and then we do more sputtering, measure photoelectrons, and go down into the material to a certain depth to get our sputter depth profile. And again, sample rotation during sputtering is very useful because it improves the quality of our depth profile. And here's an example of a sputter depth profile. This is looking through multiple layers. I got a nickel layer here. You've got a chromium metal layer. You've got a chromium oxide layer. And you have a nickel layer, a chromium layer, and here's a silicon substrate. So this is a typical sputter depth profile that as you go in and sputter, the peaks, the walls are not vertical. You would like these lines to be vertical. You would hope the interfaces are very sharp. But as you sputter, you're going to have some mixing, some roughness, and you're not going to measure sharp interfaces. Also, we're always looking at a certain depth. So we're never just looking at one layer, we're looking at certain depth. So you're always looking at the composition to a certain depth beyond the current surface. So this is a typical sputter depth profile. And as you go down, you can see the degradation in the resolution of the depth. This chromium peak almost comes up to 100%. It's about 95%, say, 97%. In this layer, it should be 100. And when you get down to this chromium layer, you can see it's only coming up to 90%. Okay, because of the roughening of the material. So as you go down, you're getting a rougher interface, rougher surface. So you're going to be seeing different depths. And if you use rotation while sputtering, you get this depth profile. And it's very different, much higher quality. You can see the interfaces are much sharper. They're more vertical. Even down here, the interfaces are much sharper. And also you can see that the chromium layer, for example, is flat topped at almost at 100% in these different layers. And also you can see the sharpness here between the chromium metal and the chromium oxide as well. So sample rotation during sputtering improves the depth resolution. And a lot of the manufacturers provide you this capability to do sample rotation while sputtering to improve the depth resolution. Now, if you're sputter depth profiling, here's an example of an organic film here. There's a 1 micrometer thick film here deposited on a calcium fluoride substrate. And this is some data that was taken by physical electronics. I want to show you the example. And they used a different kind of an ion gun. If you're working with polymers, the argon beam can really destroy your polymer. It can also destroy metal oxides. For example, if you're working with titanium oxide or tungsten oxide, the argon beam will change the chemistry. So you'll get an effect from the argon beam. So an argon beam, you must be careful, because if you change the chemistry, it'll often give, for example, if you have titanium dioxide and you sputter with an argon beam, you will see reduction in the titanium oxidation state. You will start to see some lower oxides. And that's from the argon beam. So the argon beam can change the chemistry. And an argon beam on polymers can destroy the chemistry completely. So some years ago, the companies tried to come up with different kinds of ion beams for sputtering, particularly on polymers. And a company in the UK had this carbon 60, a C60 ion gun. So Physical Electronics made an agreement with them that they could use this particular ion gun on their instruments and have an exclusive license. So nobody else could use that same ion gun on a surface analysis instrument. But the competitors, the other companies, made up their own ion guns based on different kinds of beams to get rid of this problem for looking at polymers. So they used an energetic C60 beam, rastered over a 2x2 millimeter area to create their depth profile. Now, if you've got 60 particles in the basically in the molecule, you're going to break it up when it hits the surface, and these this energy of 10 keV is going to be divided up then by these 60 carbon atoms. So the effective energy of a carbon individual atom is going to be small. Okay, it's not going to be 10 keV. It's going to be basically 1/60th of that. And this is the approximate sputtering rate that they had with this particular gun. And this just illustrates the result they got with this, this film on the calcium fluoride. So here's the sputter depth profile. I'm just showing you the main peaks, fluorine component, the carbon component, the oxygen component down here, and as a function of depth, and the calcium peak here as well for the substrate. So you've got fluorine present, you've got carbon present, you've got oxygen present in the film, and then down here is a substrate where you have a calcium coming up, and also you have fluorine still, because that's the composition of the substrate. And over here on the right-hand side shows you the spectra obtained with the C60 ion gun as a function of sputtering time. And this is 0. And as you go down and sputter, there's some surface carbon contamination, which is removed after the first cycle of sputtering. And then you have these different peaks here in your carbon corresponding to the different chemistries. And it remains stable with time sputtering. So the C60 gun is very effective in looking at these particular polymers. And down here, the fluorine peaks, fluorine, and here's the fluorine and calcium fluoride. So this is the atomic concentration of the elements as a function of the sputtering time. And down here, they've determined the components of these different carbon chemistries from their raw data and plotted those separately. So here's the carbon corresponding to CF2, carbon corresponding to CF, and the surface carbon contamination here at the bottom, going down to 0 very quickly after sputtering here for basically 1 minute. So this particular gun, the C60 gun, has been found to be quite useful for studying polymers. Today, all the manufacturers of XPS instruments now use a different kind of a gun. Physical Electronics still offers that carbon cluster, the C60 cluster beam for polymers, but now there's been a shift away from that to what is called an argon cluster ion gun. So an argon cluster ion gun is really the top line now for doing depth profiling. argon cluster. So you're using an argon cluster, and the clusters can be quite big. They can be 1,000 argon atoms in a cluster, and there might be 500. So some of the ion guns allow you to change the cluster size. So again, if you have 1,000 argon atoms in a cluster, when they hit the surface, the energy of each argon particle is going to be much lower. So you'll have 1,000 of them, and you'll sputter, but a very low energy of each one. So the sputter rate is going to be smaller, but the damage is much less. So if I take an argon cluster ion gun and sputter titanium oxide, it's not going to reduce the titanium oxide. It stays titanium oxide, which is actually fabulous. The same with tungsten oxide. It does not reduce the tungsten oxide. Now, these cluster ion guns can also be operated in the monatomic mode, where we actually have just the argon, individual argon ion, like we had in the old days, with just a simple argon ion gun. And a simple argon ion beam would change the chemistry. But if you have a pure metal, something like that, the cluster sputters very slowly. So some of the manufacturers allow you to switch in a depth profile between a cluster and a single argon ion, depending upon the layer you're looking at. So it's become quite sophisticated. So a cluster beam of argon is really the top notch now for a source, because you can use single argon ions, or you can use a cluster mode. So again here, here's an example. This is a 10 micrometer thick multi-layer polymer film, and going through the different layers. Polyethylene, polyethylene plus nylon, okay, nylon, polyethylene plus nylon, and polyethylene. And over here are the individual carbon spectra from these different layers. And you can see the intensities of the carbon in different layers. You can also see the extra peaks here from chemical shifts. So you're not destroying it. As you go down with depth, here's the surface. As you're going down with depth and going to these different layers, the chemistry is the same constant. And that's also seen over here with the spectra. You have a constant area pretty well at these different layers. Another example, so if you're working on polymers and you're doing depth profiling, this is a really nice source to have. As I mentioned on polymers, you can do angle resolve work, but it only gives you a near surface composition. You cannot measure beyond basically 3 times the inelastic mean free path. Remember, 95% of the signal comes from 3 times inelastic mean free path times the cosine of the angle of emission. So we're limited to that distance in angle resolve work. You can't go deeper than that with that work. So that's a very nice example, okay, of the cluster ion gun. So if you're buying a machine, cluster ion guns are quite expensive, but if it's in your budget, I highly recommend you get a cluster ion gun as opposed to a single ion gun of argon or a C60 source or something like that. It is so useful in many cases. The sputter rate's lower, but having the capability to use an individual argon ion as well gives you that flexibility for using a cluster when the beam affects the composition, or using just the individual argon ions when you're basically sputtering through different metallic layers where you're not going to be changing the chemistry. So that plus sample rotation gives you generally fantastic sputter depth profiles. This is just a sort of a summary of some of the polymers here taken from a data sheet, just to illustrate some of the effects that we have. This is polyethylene. I once gave a course at a chemical company in-house, And I told them this was a pretty boring spectrum. And they were upset because their whole company, the whole group was based on polyethylene. To them, that was their lifeblood. That's how they earned their salaries. So when I said it's a pretty boring spectrum, they were not happy with my comment on that. But polyethylene, a very simple spectrum, very simple polymer, basically just a single carbon peak here corresponding to in this polymer chain. Down here, polystyrene. Again, carbon bonded to hydrogen. You would expect, again, basically a single peak, but you don't. You get an extra peak down here of small intensity. Does anybody remember what this peak might be? It's not a chemical shift because it's pure polystyrene. There's no, this shift here is about 7 electron volts, which is quite big. And you need fluorine to make that shift. And there's no fluorine in the spectrum. Okay, it's pure polystyrene. Does anybody remember from yesterday what this peak is? This is a ring structure, unsaturated carbon. One of those effects I mentioned that you can have in a spectrum. Anybody remember? What was that? What was it? Graphite? No. The graphite would give you this. This is polystyrene. Graphite also gives you that peak. That might be a clue. Anybody remember? Look back in your notes, maybe. So this is sort of a summary slide to help you remember some things about the XPS. I'll just give you a minute, see if anybody can find it. I showed you an example of carbon with this kind of a peak, about this intensity, 7 electron volts away. And I mentioned what it's due to. It's not a chemical shift. And this is another source of error where people think it's a chemical shift, but it's not. It's something to do with the fact that we have unsaturated carbon. Yell it out more, I can't hear you. No, not charging, but a good example though. Could be charging. Part of the sample could be charging. It's possible that this sample is not charging. It's not from charging. It's something inherent with this particular material. No graphite. The graphite has that same. Carbide? No, not carbide. Carbide is not going to shift that much. This is a big shift. 7 electron volts is a big shift. Carbides, the shift is quite small, generally, not 7 electron volts. Okay, I'll give you a hint. No oxygen. No, there's no oxygen detected in the sample. And oxygen can't shift by 7 eV. It's too big a shift for oxygen. I'll give you a hint. It's around slide number 150. There's a hint. It's not slide 150, but it's somewhere near that. Ah, I heard that magic word. It's slide 151. It's a shake-up peak of carbon. Shake-up peak on slide 151. So slide 151, lo and behold, was actually polystyrene. I actually showed you the reference spectrum of polystyrene. Now you compare this spectrum with that one, and you can see it's very similar, right? And this is just amplified up 5 times so you can see the peak. So when you have unsaturated polymers, and particularly when you have aromatic polymers, you're going to see shake-up peaks. So this is a special effect that you get. It's the pi star shake-up, which is a 7-electron VV process. It's not a chemical shift. It's just from this particular physics that occurs in these particular polymers. So that's a shake-up peak. Okay, everybody agree? It's a shake-up peak. Again, you don't want to scratch your head and say it's a different carbon chemistry, because it's not. And here we have mylar, and mylar is more complicated. We have different carbon environments. As a matter of fact, if you look through, you'll find you have 3 different carbon environments, and you'd expect 3 carbon peaks in the spectrum. And you see essentially here 3 carbon peaks in the spectrum. And the ratios of the areas should also be as corresponding to how many carbons you have in each of these chemical environments. And here's the oxygen peak. And the oxygen has 2 different chemical environments as well. So you'd expect 2 peaks in the oxygen spectrum in mylar. So that just shows you some of the things that we talked about as sort of a summary for these polymers. Here's another example, looking at O-rings. Now, many of you are working in vacuum, and one of the posters was talking about different seals and different O-rings, different compositions, different type O-rings to use. Now, this doesn't show up very well, but it turns out that this is a fluorocarbon O-ring, and these are 2 spectra taken adjacent to a contaminant, and over here is the spectrum from the contaminant. Can you tell me what the difference is between these 2 spectra? This is from the O-ring itself, and this is from the part of the O-ring where you can see some kind of a deposit on the O-ring. And this was an O-ring that was used in transferring samples into a system. Years ago, we used to transfer through an O-ring. Today, we use a gate valve, but we use an O-ring. So there was this deposit. So what's the difference between these 2 spectra? You can see they're very different. Okay? Right, carbon is different. We also have some other peaks here. They're small in intensity, but they're labeled here as nickel and iron over here, and also oxygen. And the carbon spectrum is also more complex. So this is a fluorocarbon, carbon, fluorine, a fluorine O shape. Okay. Over here, we have some metals. So it turned out these are oxides of iron and nickel from the metal that was slid through this O-ring many times. So some of the oxide on the metal transferred to the O-ring. And you can see that contaminant then is from that metal that left that deposit on there. And down here in the bottom, you can see the carbon bonded to fluorine has a high binding energy. And this is a carbon contamination on the surface. And that also, this is a higher energy resolution of this particular region. You can see this carbon spectrum appears like a doublet. This carbon spectrum is not a doublet. And on the fluorocarbon, this is the fluorocarbon peak. So on this contaminant film, you also have carbon. And that carbon from the contaminant is the right-hand side peak, this one, a hydrocarbon peak. So you have a lot of information in here about the chemistry, what's happening in that particular deposit. Now, here's another problem for you. I want you to tell me what X-ray source they used. Did they use aluminium or did they use magnesium in taking this spectrum? How are you going to determine what X-ray source was used? Okay, I'll give you a hint in a little bit, but I want you to think about it first and tell me what X-ray source was used in generating that particular sample. Somebody said magnesium. Why did you say magnesium? Because of where the Auger peak is. Very good. Very good. If you go back to those tables, they're a little difficult to read in the notes. But remember, I told you that when you have change your X-ray source from aluminium to magnesium, the Auger peaks move. So where this Auger peak is here, I can tell it's a magnesium source. And as a matter of interest, 20 years ago, I was at a conference, the American Vacuum Society meeting, and there was a vendor there. And this vendor had this machine that they built, XPS machine, for determining thicknesses of films. And they were very secretive about it. They didn't want to tell you anything about their instrument. It was in a box. They wanted you to buy it to determine the thickness of a film. And it was designed for the semiconductor industry. And one of my colleagues who worked in the semiconductor industry was very interested in that machine, but he ended up not buying it because they would not disclose the way they determined the thickness of a film. He ended up buying a machine from another company where they had full disclosure. He knew exactly the algorithms they were using and knew what he was doing. So this manufacturer sold this machine. They still sell them, okay? And people buy them, but they don't know what they're doing. They just get an answer. They don't know how reliable it is. Well, this exhibit, they happen to have up on their exhibit a spectrum. And I asked the salesperson, I said, what X-ray source are you using in your machine? And he hummed and hawed for a little bit, and he said, oh, we're using magnesium, okay? I said, oh, that's interesting. Oh, I said, but you know what? You're wrong. You're not using that source. You know how I knew what they were using? Because in their spectrum, where the Auger peak was, I knew it was a different source. It wasn't what he told me. So the salesman, just like we worked out with this particular case here, this is magnesium source to give the Auger peak here. So the Auger peak position gives information about the source. So I told the person, no, you're not using that source. And he said to me, how do you know? Oh, I can tell from your spectrum. And he said to me, how? How can you tell from the spectrum? And I said to him, since he doesn't want to tell me anything much about the machine, I said, oh, why don't you take my course and you'll learn how to tell? Okay. Because just where that Auger peak was. So very good. So the Auger peak is the clue to your X-ray source. Okay, so there was a case of a salesman where it wasn't really supposed to disclose much, but they had a spectrum there, and he was giving me wrong information. And I didn't tell him how I knew, because he wouldn't tell customers about the algorithm, and I knew that. I pretended I wasn't an expert. They didn't know me. I just went up and said, I was curious about the machine, what can it do? And they would give me this, sales pitch. And then I'd say, oh, okay. And then I'd say, oh, what X-ray source? And I knew all this beforehand. I knew they didn't want to tell you anything. So he gave me wrong information. So I was just playing a game with him. Okay. So anyway, you can have a lot of fun in surface analysis with people, because once you know what you're doing, okay, you know exactly what's happening. And if somebody tells you something, they're wrong because of something in a spectrum. Okay, it's very interesting. Okay, a couple more examples. This is an example of from Dave Briggs, and this is a case of again a packaging film. So when you buy a package of, for example, potato chips, you go to the store, they're in bags that look very nice. So they're printed, their brands, they're printed logos on the bag. Well, the manufacturers buy these big rolls of these films, and then they turn them into packages. Then after they fill them, they seal them. Well, this is an example where they could not seal the bags. So this spectrum up the top, so what they did was they gave Dave Briggs samples of their bags, and he could look at them, the ones that seal, the ones that didn't seal, to see the difference. And this is a normal sample. This is where you had sealing, where you could seal the bags. And the lower spectrum here was from a surface where you could not seal the bags. Again, comparing the two spectra, what do you see between the two? Can you see a difference between these two spectra that might be causing a problem? So what you're going to do is look for the presence maybe of something in this particular spectrum here compared to this one. So you see a certain elements present in this one that's not present in the top one. Can you see an element present here that's not present there? Titanium, yes. This has titanium 2p doublet and titanium OG peaks. So what happened was titanium was detected on this one. And then you look and back and see what might be causing this presence of titanium. Well, the company that supplied the packaging film, the polypropylene packaging film, coated one side with a titanium containing complex to improve the printing, so they could print on the bag. And what they did was that the titanium coating was not set, it was still active. So when they rolled the polymer film, that titanium complex transferred from one side to the other in that roll. So it was not cured correctly, and the titanium transferred from one side to the other. So they knew they would expect titanium only from that particular side and not from the sealing side. So this meant that the titanium compound was transferring. So you could find the problem pretty quickly. You don't need to know the concentration. You're just comparing one spectrum with the other. There's another interesting aspect in here as well. You notice that this titanium peak here Look at the chlorine peak. See this chlorine peak here? It's been attenuated. You see that? Smaller. So the titanium overlayer is changing the intensity of this peak here. And if you look down here at this lower kinetic energy, you see the chlorine-Auger peak is not detected now. And that's because inelastic mean-free path of the low kinetic energy chlorine-Auger electrons is much shorter than the high kinetic energy chlorine-2p peak. So now the 3 lambda times the cosine of the angle is prohibiting much, signal from this particularly low energy coming through, because lambda is very small for that. Lambda is much bigger for this, and you can still detect this chlorine peak, but not that one. So that could be another complication looking for confirming peaks. That if you have an overlayer, the high kinetic energy peak you might detect, but the low kinetic energy peak you don't detect because of its shorter inelastic mean-free path. You can't look for that same thickness in a material. And if you're buying a machine, again, like Auger spectroscopy, a lot of things to consider. What kind of an X-ray source do you want? Do you want a twin or a dual anode? Do you want magnesium or aluminum? Do you want a monochromatic source where you have no satellite peaks and no bremsstrahlung? Do you want a hard X-ray source to look deeper into the material? Okay. So manufacturers can provide different options. I think I mentioned yesterday, one of the machines I use had 4 X-ray sources. It had a dual anode, aluminium and magnesium, where you're going to have satellite peaks in the spectrum, monochromatic aluminium, and monochromatic silver to give me a harder X-ray source. So I could determine the thickness of the film like I showed you in the case of germanium, if you remember that. What type of energy analyzer? In XPS, most of the manufacturers use the hemispherical analyzer, which is a beautiful analyzer. How do they detect the electrons? What kind of spatial resolution do they have? Do you need a higher spatial resolution? Do you need imaging capability? Do you need angle resolve XPS capability? Do you need an ion gun for sputter depth profiling? And if so, it'd be very nice to get one of these cluster argon guns. Sample size. How large a sample can you introduce into your system? One of the manufacturers sells an instrument for looking at 12-inch wafers. Okay, it's a special option, one of their machines, that they can look at 12-inch wafers. Heating and cooling of a sample, particularly in situ, so you can study diffusion without moving your sample. So you're always looking at the same place. What kind of charge control is provided? I mentioned about low energy electron beam. I also mentioned the possibility of using a low energy ion beam. What kind of vacuum pumps do you want? What kind of operating pressure? You want ultra-high vacuum. You're doing depth profiling on reactive materials like titanium or tungsten. You don't want the background gases contaminating your surface while you're acquiring your data. So you need ultra-high vacuum. And the vacuum pumps, you don't want oils and so forth getting into your chamber. And most of the instruments today, not all of them, but most of them use an ion pump in the analysis chamber, and also perhaps a titanium sublimation pump to improve the vacuum. The degree of automation. When I started off in XPS, everything was on paper, as I mentioned. Today, we have computers. How automated do you want it? Also, do analyses. Can you select points, like on a sample? You always want to analyze at least 3 points on a sample, even though you think it's uniform, to verify that it's uniform, that you get the same composition. So always do at least 3 points. So you can select these places with the computer, and you can select many places with the computer. So you can have the machine running all day, all night, looking at different places on samples, doing depth profiles automatically, and so forth. I mentioned I don't normally do mapping, but machines that have a high degree of automation allow you to use them 24 hours a day and also on the weekend. And some machines allow you to access them from home. So if you want to, you can check on your data. You can do things from home. Also check on your results, see if it's working okay and things like that. Don't forget, you don't want to spend all your time in the lab. You need a home life as well, but you can access the machines remotely. What kind of data processing capabilities? If you don't particularly like their data processing capabilities, but you like everything else, you can buy a third-party software package to process your data. How reliable is the instrument? You want it to be reliable. You don't want it breaking down every day. And what about maintenance? Can you get good maintenance on it? Spare parts. Back in the 1970s and 80s, we had a machine from the United Kingdom, and when the machine was delivered, it turned out they had a small leak, small crack on a well. So the system didn't evacuate well. Okay, so they shipped it from England, and it was on a large arm. And that well, with all the vibrations and everything on the flight and packaging and shipping by road and everything, caused a small crack in the well. Well, at our facility, in another building, we had the capability of using heliarc welding. So we told them we can have that fixed. Well, they said, no, we're going to ship it back to the UK and have it fixed. And that's what they did. They shipped the instrument back to the UK to do the welding and shipped it back to our lab. So maintenance, also that company back then, all their spare parts were kept in the UK. So if you wanted a replacement anode in your X-ray source, they had to have it sent from the United Kingdom. So they didn't have many instruments in the US, and they didn't keep many spare parts in the US. Today, that same company has all their parts, a lot of maintenance and everything in the US. But back in the 70s and 80s, they did not. And of course, you can't always believe them. You always want to talk to people that have bought the machines and discuss that with those people, and send the test samples to the manufacturer's facility and ideally visit it to see how good they are. Okay. So, and they normally do analysis for you for free because they want to sell you an instrument. Instruments cost, they vary from $500,000 US to $3 million US, depending on what you want. So a big range of prices on machines, a big range in automation, also between machines. Now, general summary for XPS, the sensitivity from lithium up, it's very specific. We normally have no problem identifying the elements that are present. But remember, be very careful about shake-up and these kind of features that occur in spectra as to where they come from and not other compounds. The variation in sensitivity factor is about 100. So as I said, if you're looking at lithium fluoride, the lithium peak is going to be about 100th the area of the fluorine peak. Yet they're equal concentrations. So remember, some elements give you big peaks, some elements give you small peaks. And in the same element, pure element, different shells give you different intensities. Detection limit, about 0.1 to 1 atomic percent. Spatial resolution, a few micrometers for most systems today. But if you want higher spatial resolution, the best you can get today is 0.1 micrometers at a synchrotron. The analysis depth depends upon the material and the photoelectron kinetic energy. In other words, material and inelastic mean free path of your photoelectron peaks, signals. It's about 10 nanometers. And you can spud depth profile for greater depths. Quantitative, homogeneous samples are much easier, but you need reliable sensitivity factors. And XPS, we don't have that backscattering like we had in OJ spectroscopy from electron beam. X-rays don't backscatter. So it's much easier to quantify peak areas. And also, we have simpler spectra in XPS compared to the OJ spectra. The chemical information, chemical shift, very useful. OJ parameter, also very useful. But again, remember, you're going to have possible beam damage. And generally it's lowest with monochromatic source for in XPS. Okay, so let's see. So that really ends the XPS part. We're oh, very nice. We're a little bit ahead of time, 15 minutes or so ahead. So I'd like to maybe continue. Oh, you want to stop? Tea break? Tea break? Yeah. And then come back? Yeah, we'll be back. Have a longer section, 11:15. Okay. Yeah. So we'll come back at 11:15, and then we're going to talk about some ion spectroscopies. Now, I mentioned to you that years ago, I used some ion spectroscopies. I used ion scattering spectroscopy, and I've done some work on SIMS a long time ago. But I don't do SIMS currently, and I don't use backscattering spectroscopy either. But I want to include these in the course for your knowledge. Okay? So I'm not an expert in these areas. Ion scattering I've done, I know about that. Okay? But the SIMS I know a lot about as well, but I don't do it. Okay? RBS, I know a lot about it, but I don't do it. Okay? So I want you to understand these techniques because they're fantastic techniques that you can access. And in the back of the notes, there's a few publications that are included on the different techniques. So there's articles in the back on OJ spectroscopy, XPS, ion scattering spectroscopy, SIMS, RBS, even nuclear reactions. Nuclear reactions are also used for near surface measurements. Okay, so in the back, there's some papers that have been published here, and they're for educational purposes, so there's no really copyright issues. There are also articles here about the scanning Conley microscope and things like that we're going to talk about later as well. So you can read more details about those techniques also in these articles in the back. Okay, so take a break.
Thank you very much, sir.
Okay.
It was really nice. So now we have a tea break. So you are requested to come back like 11:15. So we will start our last session. So please proceed for the tea break. At the end of this session, we have a lunch break. And after the lunch break, at 2:30, we have a closing ceremony. So please make sure to be here after lunch at 2:30. And there is another announcement. We have circulated a sheet for your attendance. So if you have not yet endorsed your attendance, please come put it here so that we can arrange the distribution of the certificates. So now we start our next session. That's probably on the ion spectroscopies. So please have a seat.
Okay, thank you. Okay, welcome back. So now we're going to talk about some of the ion spectroscopies. I'm going to start off talking about ion scattering spectroscopy, then SIMS, a variation of SIMS called SNMS, and Rutherford backscattering spectroscopy. And then after that, I'm going to talk about some other techniques as well, just very briefly. So ion scattering spectroscopy uses a low energy monoenergetic ion beam as a probe. And the ions are elastically scattered from the surface. And some of them remain as ions after leaving the surface. So when an ion interacts with the surface, there's a high probability that it's going to be neutralized by the surface of a material. But some of the ions that are scattered, okay, will be scattered as ions. And those are the ones we're going to look at. So we're looking at the same species that we're using in the beam. So it's a scattering technique. And we measure the energy distribution of these scattered ions to determine the surface composition. And you'll see this technique, ion scattering spectroscopy, called ISS or IS, is the most surface sensitive technique of all. Ion scattering spectroscopy, by using inert gas ions, basically just looks at the top atomic layer. You don't even see the second layer. The reason is that if the ions penetrate into the material, they're going to be neutralized. So only a small fraction of the ions that are scattered remain as ions, and they're scattered from the surface. Those that penetrate are going to be neutralized. So we're looking at the same species that comes in. So if we're using a helium beam of ions, we're going to look at the helium ions coming off the surface, the same species. Okay. And the energy distribution of the scattered ions determines the surface composition. SIMS is secondary ion mass spectrometry. We use an ion beam as a probe, but in this case, we're looking at the species coming out of the sample. So they're called secondary ions because the primary ion beam comes in and produces ions from the sample. That's why they're called secondary ions, because they're produced from the sample. So we're examining the ions that come out of the sample. And some species are sputtered as ions, but most of the particles that are sputtered are going to be neutrals. So there's a variation of SIMS. The secondary ions we're looking at in SIMS, and we can look at the positive ions or the negative ions, but most of the particles coming out of the sample are going to be neutral particles. So if you could ionize those neutral particles that come off the surface, you're going to have a much more quantitative, much more representative composition than by looking at the ions coming off. And that's called SNMS, where we're measuring the neutrals. It's a neutral mass spectrometry, and I'll talk about that as well. But in SIMS, we're looking at the mass to charge ratio to determine the composition of the surface. And SIMS is there's a very high detection limit, much higher detection limit than Auger spectroscopy or XPS. That's one of the main advantages for SIMS. You can look at parts per million or parts per billion of an element in a material with SIMS. In Rutherford backscattering spectrometry, use a very high energy ion beam as a probe, and you're looking at the same ions as they're backscattered from the sample. So those ions are backscattered by the nuclei in the sample, and those that are backscattered are measured and determines the composition and depth distribution up to a depth of about 1 micrometer. So I'm going to illustrate some these different techniques here and some examples so you can see how useful they are in analyzing materials. So ion scattering spectroscopy, the process is shown here. We have an incoming ion of a certain mass M, has a certain primary energy, EP, that's the beam energy, and the ion comes in and scatters off an atom in the surface. So after scattering, it will have an energy E, but it still has the same mass because it's the same species. And some of the energy is transferred to this atom in the material, and but the ion is scattered, and it's scattered through a certain angle. So this is the incident beam direction, and this is the exiting beam direction. So that ion has been scattered through this angle theta here. So that's also an important feature, the angle of scattering. So we're looking at the same species. We use inert gas ions, the most commonly used for ion scattering spectroscopy, although in some cases people use alkali ion beams, but the gases we normally use are helium and neon. And you'll see why we need both these gases to do ion scattering spectroscopy. Just a little bit here in ion scattering spectroscopy, and looking at the energy of the scattered ion. Up here's what I showed you in the previous slide. Use the conservation of energy and conservation of momentum, but consider only single scattering. It's possible you might have multiple scattering, but single scattering, this is the equation you get comparing the energy of the ion that's scattered to the energy of the primary beam. M atom, M ion, this is the atom in the material, and theta is the scattering angle. So it's a rather complex equation here. But if the scattering angle is 90 degrees, this equation simplifies quite a lot. And this is for 90-degree scattering. The energy of the scattered ion compared to the primary ion is simply the mass of the atom in the surface minus the mass of the ion that you're using as a probe divided by the sum of those same masses. So it becomes a very simple equation. This equation shows you for 90-degree scattering, the mass of the atom that you're looking at has to be greater than the mass of the ion that you're using to get a positive number. This means that if I use an argon ion, I can only look at atoms in the surface that have a mass greater than argon. So I could not study light elements. I could not study oxygen, for example, in ion scattering spectroscopy. So when you want to study the light elements, when M atom is small, we need a low mass ion. And this is why it's important to have a helium beam. So we use a helium beam to be able to basically study the light elements. And you'll see later that we also want a different ion to separate out the different peaks from heavier elements, because after a certain time, when you get to a certain atomic number, certain mass, all those particles look heavy for an incoming helium ion. So you want to use a different ion as well. So to do ion scattering spectroscopy, you need a light ion for looking at the light elements, and you need a heavier ion to separate out the masses of the heavier elements. I'm going to show you that. And that's described here in this slide about the need for the low mass ion beam, typically a helium ion beam for detecting the light elements, and then a heavier ion like neon to detect the heavier elements. And the ion scattering spectroscopy is also sometimes called LEIS, low energy ion scattering. So these basically are the same technique, just different terms that are used by different researchers. And in publications, people use either one of these particular terms. So here's an example of an ion scattering spectrum. This is on mica. This actually was in a commercial instruments made by 3M company. And they also use this cylindrical mirror analyzer, like I showed you, is often used for Auger spectroscopy. But in this case, they put a coaxial ion gun inside in a cylinder rather than an electron beam. Remember, I showed you the case where they had an electron beam inside. So 3M company made this analyzer with an ion beam inside for doing ion scattering. So here's a spectrum from mica, and this was obtained using a helium beam. So you're measuring this ratio of the energy of the scattered helium ion compared to the energy of the primary ion. And you can see the separation here of these different elements. Okay, and you can see oxygen, you can see fluorine, sodium and aluminum here are overlapping to some extent, and you can see also the potassium. The reason that you need a secondary species is illustrated here. This is a spectrum from an alloy of iron, molybdenum, and rhenium. So if you're using a light ion beam like helium, you see you get two peaks and a shoulder. This is iron, this is molybdenum, this is rhenium. So you're not resolving these peaks because these elements are fairly heavy compared to a light helium ion. So this is why you need another ion like neon. So neon gives you this spectrum where now you can separate out these three components on the surface very clearly. An iron peak, a molybdenum peak, which basically goes up higher by a factor of 2, and rhenium. So you separate out these three species, and that's why you need these two different ion beams. The helium is needed for the light elements, and the neon is needed to separate out these heavier elements. So you wouldn't know necessarily what these elements were because of all these overlap issues here, that the scattered beam energy is very similar for a lot of these particular species. This is perhaps the most important slide for ion scattering spectroscopy. You can take a crystal of zinc sulfide and you can get orientations of these two different surfaces. That one side is going to have in the top layer just zinc atoms. And on the other side of the sample, just sulfur atoms in the top layers. Outermost layers just have the one element. So if I was using Auger spectroscopy or XPS, I'm going to see signals from both the zinc and the sulfur because of the inelastic mean free path. I'm looking at several atomic layers. But if I use ion scattering spectroscopy and look at the spectra you get from these two different faces, one side, shown here by the dashed line, is essentially giving me just sulfur. And the other side of the crystal is giving me just zinc. This extra peak here is from double scattering, where the ion is scattered by two surface atoms of zinc. And this is obtained with neon. And you can see the surface sensitivity of the technique. It is so surface sensitive that you don't even see the second layer. Now, of course, if the ion beam is left on, you do some sputtering with it, you will actually see the second layer. So it's very important to realize that you must have a very low current density of your ion beam if you want to do true ion scattering spectroscopy and just look at the top layer. The effect of sputtering is shown here. This is a study of barium on tungsten. Now, tungsten impregnated with barium is used as a cathode electron source. And one of the theories of the emission of these electrons from these cathodes is that you will have a layer of barium on the surface of tungsten. So you have a porous tungsten plug impregnated with barium. And when you heat it, the barium will diffuse to the surface and reduce the work function and give you electron emission. So one of my colleagues, Bill Bourne, thought he would do an ion scattering spectroscopy study to see if this is really true. So on the left-hand side here shows you his initial results using a 1,500 volt beam of neon ions. And down here, the surface before heating. And you can see only a small peak from barium and a large peak from tungsten. Now, remember, I told you about sensitivity factors, and be careful about saying peak is small, you have a low concentration. But ion scattering spectroscopy is basically looking at the top layer. So you can see here that you're seeing tungsten, but the barium intensity is very small. So if barium is diffusing to the surface and forming a layer on the surface, it doesn't look like that's the mechanism. So on heating it to produce the barium on the surface, the spectra are very similar. So this is the current through the filament in this emitter, but the spectra are very similar. But this problem here is the fact that the beam energy that was used and the current density was a little high and was sputtering the barium from the surface. So in ion scattering spectroscopy, you must be careful. You want to use a low beam energy of the ion, and you must use a low current density, otherwise you can sputter the material while taking your spectrum. And on the right-hand side, it shows you the same kind of emitter, but now using a much lower beam voltage, it's 300 volt beam of neon. But now you can see that the barium signal is dominant, and the barium is indeed at the surface when this emitter is working. So sputtering is an issue. You must get a detectable signal, and you must also be careful not to sputter away the surface layer. That's one of the most important things in ion scattering spectroscopy, is to make sure you're not causing a problem with the scattering. Okay. The instrumentation, it can also be performed in many XPS instruments. For example, most XPS instruments sold have a capability of using ion scattering spectroscopy. Okay? Because basically you're looking at an ion instead of an electron. So you have to reverse the polarity of your analyzer to measure a positive particle instead of electron. So the polarity of the electron energy analyzer, that's normally used for XPS, for example, can be reversed to measure these positively charged ions coming off this material. And I showed you yesterday an image or a picture of one of the machines I had. I mentioned that ion gun had several ion gases on there, several gases I could use, and that's specifically for doing ion scattering spectroscopy in that XPS instrument. But special instruments have been designed for ion scattering spectroscopy. I showed you the cylindrical mirror analyzer with the coaxial ion gun. Also, a lot of work was done using 127 degrees cylindrical sector analyzer. But there's a new one that was developed based on a double toroidal analyzer. And this is sold commercially today for doing excellent ion scattering spectroscopy work. And that particular instrument is shown here. On the right-hand side is the instrument that's sold. It's sold by IonTop, who also sells SIMS instruments. And this is the analyzer. So you have a beam coming through here onto the sample, and you have this large 360-degree azimuth range for measuring your scattered ions. So this allows you to use a very low current density to take an ion scattering spectrum, so you're not going to have significant sputtering to acquire a very good spectrum in ion scattering spectroscopy. So this is designed specifically for ion scattering spectroscopy. Now, if you want to do depth profiling, you basically need two ion beams. You need one for ion scattering spectroscopy, and you also need one for sputtering. So this is the beam, the neon beam here used for ion scattering spectroscopy, for looking at the heavier elements. And here is the ion beam that's used for sputtering. So this one's going to have a higher current density. It's going to allow you to sputter. And then you can measure the surface after sputtering with this other beam. And that toroidal analyzer I just showed you, the current density can be quite low. So even using a high energy beam is not going to cause significant sputtering during the acquisition of the data. So here's an example of chromium nickel multilayers taken with this particular system. So this is the ion scattering spectrum depth profile. So at the beginning, chromium is not detected. Chromium is the top layer. Nickel is the layer below. So before sputtering, chromium is not detected at all because of surface contamination. But in Auger spectroscopy and XPS, you would see the chromium because you're getting a signal from the chromium because you're looking at a certain depth of analysis. But ion scattering spectroscopy is looking at the top layer. So you don't get any chromium signal to start with. Then after sputtering and measuring your ion scattering spectrum, you see the chromium layer. And as you alternate sputtering and analysis and go through these layers, eventually the chromium layer is going down and the nickel layer is coming up. But again, you're going to have some degree of roughness after sputtering. That's an issue again of with the depth resolution. But it shows you the depth profile by using these two different beams, looking at the top layer at one time. So ion scattering spectroscopy is a technique for looking at the top layer, just the top layer, if it's operated correctly. So you don't want to sputter material away during your analysis. And you need the different ion species, as I showed you. Helium and neon, for example, are commonly used to detect light elements and then mass resolve the heavier elements. So you can detect from about lithium up to heavier elements, and the sensitivity generally increases with the heavier elements in the sample. You can also study surface crystallography with ion scattering spectroscopy, and this has been done where people determine the crystal structure at the surface using ion scattering spectroscopy. And a lot of this work was done back in the 1970s and published. Other people also used alkali ions to probe deeper into the material. But today, if you want to do ion scattering spectroscopy, you're going to use one of these type of instruments with helium and neon beams to do your analysis. So that's just a summary about ion scattering spectroscopy. Extremely useful technique. And as I mentioned, you can do it in an XPS instrument because they can reverse the polarity of your analyzer, and all you need are different gases in your ion gun to do the measurements. Okay, so just some comments here about the technique called SIMS, secondary ion mass spectrometry. We're using a beam of ions once again. There's an ion coming in here in black. This ion is generally a high energy, and the ion comes in and loses energy in the material, scatters, and can eject species. It can eject atoms, It can eject molecules and also different mechanisms for sputtering. But you're looking at the species coming off. And despite this figure I borrowed from somebody, it's not a Mickey Mouse technique. Okay. It's a real science technique. So the species coming off are generally neutral particles. Most of the particles coming out of the sample are neutrals. But some come out as positive ions and some come out as negative ions. So in secondary ion mass spectrometry, we're looking at the ions. And we can take spectra of the negative ions and the positive ions that come out. And with SIMS, we're removing material. So we're removing material from the sample to do our analysis. So it's destructive. So by sputtering with different beams, argon's been used for SIMS. Oxygen's also been used for SIMS. Cesium, gallium, SF6, gold. Beams of gold have been used. And bismuth is also used in SIMS. So the early SIMS work was done with argon. Later, people found that oxygen beams were also very useful. And then cesium beams. And then other type materials also were used in SIMS. So today, people often use gold and bismuth beams. We're looking at the species emitted from the sample. As I mentioned, they're mostly neutral, but we're looking at the positive or the negative ions in doing our SIMS study and measure their mass to charge ratio. M over Z is measured to determine the composition. So you can see if you have a certain mass that's sputtered of a certain species, it could be an atom, it could be a molecule, you divide by the charge. So if the charge is 2, it's going to appear at a ratio of a half of what you would expect for that particular species coming off. So here's a very simple SIM spectrum from pure silicon, okay, showing you what you get in a typical spectrum as either a positive ions up the top and negative ions down the bottom. So this is the mass to charge ratio, and here's silicon. So this is a single ion of silicon. This is Si2, Si3, Si4, Si5. So different cluster sizes of the species coming off the surface. You'll also notice there's a peak of half the mass. So this is silicon doubly charged, single atom, but doubly charged. So M over Z is a half of what it would be for silicon plus. This is also a logarithmic scale. So the intensities vary quite significantly for these different species. This is the negative ion spectrum, showing you silicon minus, silicon 2 minus, and so forth. So the spectra are quite different, and the intensities are also quite different. So you can do a positive ion spectrum and negative ion spectrum. And the question is, why would you do one versus the other? Here's an example also. This is a mixed oxide, vanadium and iron oxides. So on the left-hand side are the peaks you get, the mass to charge ratios plotted here for different combinations of the components, vanadium, iron, and oxygen. So you get lots of different possibilities of the species that have been sputtered from the surface. They've identified here each of these individual signals. And also, after reaching equilibrium, after you sputter for a certain time, you'll reach equilibrium concentration on the surface. That is shown here by the dashes. And then if you expose the surface to oxygen, you can see the intensities are different. So when you oxidize the surface, the intensities can vary, and they can vary quite significantly. Oxygen normally enhances the ions that you detect. Here on the right-hand side, the same material, but this is the negative ion spectrum. And you can see here, the black lines, okay, represent the oxygen covered, and the dashed lines represent those that you get from the basically sputtered species. Now, the secondary ion yield you get varies depending upon whether you've got a clean surface or an oxide surface. So if you're looking at the positive SIM spectrum, the positive ions, the intensities change enormously when you have oxygen present in the surface. So this is a table showing you different metals and the yield, what's the signal intensity of the positive ions coming off these pure materials. So this is the number of ions coming off per incident ion. And you can see it's quite small. Now, if you take these same materials but oxidize the surface, you can see the signal, the yield increases enormously. Okay, so it increases enormously. So a lot of the early instruments for SIMS had a tube coming into the instrument where you could put oxygen directly onto the sample surface. So there was a tube coming in where you could supply oxygen that would spray onto the surface during your analysis to try to oxidize the surface to give you a bigger signal. Then people thought, why don't we use an oxygen beam? So people use an oxygen beam to enhance the signal. So the oxygen from the beam is oxidizing the surface and giving you a bigger signal. But I think you can see from this that the quantitative capability of SIMS is extremely difficult on these kinds of materials because the number of ions coming off per incident ion depends on the chemistry. So in general, for simple SIMS measurements of complex materials, quantitative analysis is almost impossible because of this fact. And the ion yield is shown here for positive ions and negative ions. So the positive ion signals, this is logarithmic again. So the alkali metals, for example, have a high relative intensity. And conversely, for the negative ions, elements like sulfur and so forth have a high intensity. And if you compare these, they're basically inverted. Most of the elements, some will have a high signal for positive ions and some will have a high signal for negative ions. So if you're looking at a surface perhaps of iridium or platinum or gold, here you can see gold. Yeah, it's right down the bottom here in the positive ion spectrum. Whereas in the negative ion spectrum, gold is a high sensitivity. So this illustrates the difference between different species and why you'd want to use a positive ion spectrum and a negative ion spectrum to learn more about your sample. So the instruments normally use both of these, a positive spectrum and negative spectrum, for these different species you might be examining in a SIMS analysis. So another aspect of SIMS, besides using different kinds of ion sources, we have two terms associated with SIMS. One is called static SIMS, and one is called dynamic SIMS. Static SIMS means I want to examine the surface without changing the composition. So I want to sputter away basically less than 1% of the surface atoms. So I get a signal that's representative of this surface. So I am removing atoms, but if I remove 1%, the surface is still intact. So static SIMS refers to a surface analysis, where you're removing less than 1% of the surface atoms to do your analysis. And some instruments are designed specifically to do static SIMS. Another instrument is designed to do dynamic SIMS, where you're doing depth profiling, where you're analyzing the depth distribution of elements. And this is very commonly used for looking at implants in semiconductors, in the semiconductor industry. You're looking at the depth distribution of elements in the semiconductor. This is looking at the surface composition. This is looking at the depth profile. We also have a choice of different mass spectrometers. The early SIMS instruments used quadrupole mass spectrometers, but these have limited mass range and limited mass resolution. Magnetic spectrometers also used. These are very good mass spectrometers, and time of flight mass spectrometers are used. So in a static SIMS instrument, a lot of the people use time of flight mass spectrometry. And the dynamic SIMS, where you're profiling, you use a magnetic spectrometer because you're getting many ions off as you're sputtering. So you can scan your magnetic spectrometer to obtain a depth profile. So it's quite complicated in terms of what kind of instrument you want to use. Now, I remember a long time ago when I was teaching courses in surface analysis, just general courses talking about different techniques and talking about SIMS. One of the students came up to me afterwards and said, now I understand why they fired so-and-so. This person bought a SIMS instrument and it didn't do the job that they wanted. So the company fired the person. The other person that came in to operate the machine, they sent to a course, and he found out why, because basically the slide. And they bought the wrong instrument. Okay, they wanted to do depth profiling, and they bought a static SIM system, which was basically designed just look at the surface. And most of the time, you don't really, a static SIMS instrument, you can do sputter depth profiling now in these instruments. But the ironic thing is that the person that bought the instrument didn't really understand the technique and didn't send a sample to the manufacturer to see if they could do the analysis they wanted. But the interesting thing is that that same company that sold the person the machine made both type instruments. They made a static SIMS and a dynamic SIMS. So it wasn't a matter of a company coming in and taking away a sale from another company, which also happens. I've seen this happen where a company came in, took somebody out to dinner, and the next day they changed their mind, must have been a really nice dinner, and bought a different machine. And the one they bought was the wrong one. The original one they thought they wanted was the correct one. And they couldn't do any analysis that they wanted in this machine. But the reason they bought the wrong machine, the person thought, oh, this brochure has beautiful pictures in it. And it costs a lot more. So it has to be better. So they bought the machine based on the fact it had nice images, and also it was more expensive. So they figured it had to be a better machine. Okay, so it was not the right machine. So things like this happen, and I've seen it happen many times where people buy the wrong machine. The same with the techniques. I've had people come in and say, oh, I want to do an XPS analysis on this sample. And I'll say, oh, what do you want to learn? And that's the most important thing in doing analysis. what do you want to learn? And when they told me what they want to learn, I said, oh, XPS is not the right technique for that. One of the other techniques is what you want. But see, somebody told them, you need to do XPS analysis on it. So knowing how these different techniques work and what you can study with them is extremely important. So you can answer the problem you want the best way you can. And if you don't happen to have the instrument, you can contact somebody maybe who has one, or you could pay for a service where they could do that analysis for you. So there are many SIMS instruments available. And SIMS has been around for decades and many types of instruments. Now, here's an example, it's a table here of detection limits. And this is a dynamic SIMS looking at depth profiling, particularly implants in semiconductors. What kind of a detection limit can you get? And the detection limit is incredible. This is parts per million atomic. So you can look at parts per billion of certain species with SIMS. Because SIMS doesn't have a background like you do in Auger spectroscopy or XPS. You don't have that continuum of background. You only have signals coming out at specific mass to charge ratios. So you have no background to worry about. So you have a high detectability. So SIMS is extremely high detectability compared to the other techniques, and very useful, particularly at looking at implants. And this example here is an example using an oxygen beam, where you're enhancing also the sensitivity with an oxygen beam in doing your analysis. Here's an example of some depth profiles. So this is dynamic SIMS, and comparing 3 different implant doses. And you can see here the depth distribution of the implant. This is a silicon sample. And this is arsenic implanted into silicon. And this is the depth profile you get. And you can see the high dynamic range. You can see the detection from higher concentrations, factor of 10, 100, 1,000 lower. So you have this so-called high dynamic range. You can detect higher concentrations, you can detect lower concentrations very easily because you don't have this background. And the question is, what species ion to examine? So in these depth profiles, they looked at the arsenic oxygen ion. So they used the beam of oxygen, and they looked at an arsenic plus an oxygen in their SIMS analysis. So they set their spectrometer up to look at the arsenic oxygen negative ion and do their depth profile then looking at this particular arsenic species. And this over here is that arsenic oxygen negative ion for doing their depth profiling. And these results in SIMS are beautiful agreement with theoretical projected ranges and so forth of implants in materials. Very nice. So one question that arises in SIMS is that sometimes you might have peaks that have very similar mass to charge ratios. So you also have that question, like in the other techniques also, about resolution. In this case, mass to charge ratio resolution. I just want to illustrate this here by, again, another implant. This is a phosphorus implant. And looking at the phosphorus implant, this is taken an instrument that has a high mass resolution of 4,000. And this is the one using magnetic spectrometer. Give you a very good mass resolution and looking at the phosphorus peak in the implant. And here's your implant. This is the phosphorus intensity. And you're going down here with depth down to the detection limit. So you've got a range of intensities again, log scale, 10, 100, 1,000, 10,000, 100,000 range of intensities of that signal. This is a high mass resolution. Now, in silicon, if there's hydrogen around, or if you have hydrogen in your silicon, if it's hydrated silicon, there's also a peak also at approximately the same mass charge ratio. So if you have that present, you're going to have an overlap problem here at mass 31. Okay? So silicon hydrogen is mass 31 and phosphorus mass 31 are close in mass. So if you did not have a high mass resolution, once you go through and take your phosphorus profile, this is the silicon hydrogen measurement during a profile, you would only go down to this level, because then the silicon hydrogen signal is going to be the dominant signal, and you couldn't measure these lower concentrations. So mass resolution is important. If you don't have that capability, you might be able to use a different species. So instead of using certain phosphorus species here, phosphorus 31 plus, you might use a negative ion or a negative molecule instead. So this comes from experience and so forth in the SIMS field as to what species you want to look at in doing your depth profile to get the best possible depth profile that you can. This is just an example of a Langmuir-Blodgett set of films here, using again a C60 beam. I mentioned the C60 beam earlier, and useful beam for looking at polymers. So they're looking at the signal coming off using this particular beam here, and you can see these three layers on a silicon substrate. And you can see here the signal going through these different layers here in this particular Langmuir-Blodgett film. And this is from a paper by Nick Winograd and some of his students. Nick Winograd is one of the basically grandfathers of SIMS. He did a lot of work on SIMS, developing his own instruments, understanding what SIMS is and so forth. Okay, but you can look at also polymers with the SIMS technique. Spatial resolution, you can also do mapping across a surface. And this is just an example of spatial resolution. This is a special reference material. It's a certified reference material, and there's several different kinds that are used for SIMS. So you can measure your spatial resolution. You can also use these for spatial resolution in Auger spectroscopy and in XPS, the same kinds of things. So some of these layers have aluminium in them. So if you're looking at the aluminium signal, and here's looking across part of this reference material, where it's bright here is the aluminium plus secondary ion coming off. And you can see as you scan across this particular reference material and form a map, a two-dimensional map, you can see these bars where the aluminium is present. And here you can see the signal is lower, but you can almost resolve the fact that there are three regions here that are close together. Over here, it's hard to see, but there is some low intensity signal here. And up here are line scans across these different parts here at different times, or summing up the line scans to get better signal to noise. So this is basically one line scan. And this is a sum here of B of 5 lines. And down the bottom here, this happens to be 256 lines for a better signal to noise. So you can see here the spatial resolution here across these different aluminium containing regions. And here you're not resolving completely these, but you can see it looks like there are 3 different regions here, but they're overlapping. And down here, you're getting a much smaller signal. Over here, the same, and so forth. So it just shows you the 2-dimensional imaging that you can do in SIMS. But in SIMS, you can also do 3-dimensional imaging. So in dynamic SIMS, where you're sputtering material, it's possible to obtain lots of information that relates to where the ion beam is and to depth. So you can form 3-dimensional imaging in SIMS. And on the left-hand side here, just shows you the counts of different components in this material. And over here, the surface compositions of silicon, aluminium, and also signals from different species that you have. And you can see how these are complementary. So the surfaces are mixtures of silicon and silicon dioxide. And you can see where the silicon is, you've also got the aluminum oxide present. Okay, and it's complementary also to the metal part. In the middle, these are the 2-dimensional maps you get, and down deeper, the 2-dimensional map deeper down. Well, you can measure these 2-dimensional maps by scanning your probing beam and keeping information about where the beam is and the depth. And after you take your data, you can reconstruct these 3-dimensional images of the different components in your material. So this is another common use of SIMS, is to obtain a 3-dimensional information about species into a material with the technique. Here's an instrument designed specifically for doing static SIMS. And this instrument uses the time of flight technique. There's a tube here that times how long the ion takes to get from the surface to the detector. So the ions that are light, okay, have a higher speed than the heavier ones. So by timing them, you can take a spectra by just counting the time. The species come in and you measure the time. So it's the time of flight, the time it takes for the different species to like fly up and fly back down in this particular spectrometer. So it's called time of flight mass spectrometer. So you just sit there and count the time. So that's a static SIMS instrument. The dynamic SIMS instruments are often this particular type. This is Kamika. This is designed for sputter depth profiling, where you're continually sputtering and measuring your species. So these are different manufacturers, and they're concentrated on these different types of machines. Now, one of the companies in the United States that does a lot of analysis clients and SIMS, they have 30 of these machines. 30 of these machines. They're looking at so many different implants, so many different wafers, so many different characterizations for a number of semiconductor companies. And over the years, they kept buying more machines. So they can keep 30 machines running, and they need 30 operators really also, essentially, one for each machine really. This shows you the demand for these kinds of analyses, to understand the implants, to validate the implants that they're making in their semiconductors. So SIMS is incredible mainly because you can get high sensitivity. Now, a couple of the other things I didn't mention about SIMS, it's also good because you can detect all the elements, including hydrogen, with SIMS. So you can detect hydrogen directly with SIMS. Another important aspect is you can detect isotopes with SIMS as well. So this is a very important area as well. So you can use a different isotope of oxygen in your beam compared to what you would normally have in an oxide. So you can distinguish oxygen from your beam versus oxygen from your sample by using an isotopic oxygen beam, okay, with the lower concentration isotope of oxygen. So this is also useful. And a very high sensitivity, parts per million or parts per billion. Whereas in OJ spectroscopy and XPS, we're limited to about 0.1 to 1 atomic percent in doing our analysis. Surface analysis uses static SIMS, and depth profiling uses dynamic SIMS. Okay, so that's very important to remember. I mentioned to you that most of the species coming off the surface are neutrals. So if you could use the neutrals to study the neutrals, you're going to have a much lower effect of the matrix. You're not going to have these large variations in intensity that I showed you when you have an oxide versus a metal. So most of the species coming off are neutrals. So there is a way to produce a spectrum of these neutrals by ionizing them. So when these neutrals come off, what you want to do is get rid of the ions. You can use a high potential to get rid of the ions, and then you have the neutrals. And then you want to ionize the neutrals. And once you ionize the neutrals, you use a standard SIMS procedure to measure those ionized species. So this is the sputtered neutral mass spectrometry, SNMS. So we're looking at the sputtered neutrals that leave the sample instead of the ionized species. So these neutral particles are post-ionized. So after they come off, we're ionizing these neutrals. And the different ways to ionize them. People ionize them using electrons, plasmas. Plasmas are also used to ionize the neutrals, or even lasers. Depends upon what your needs are. And in the case of lasers, a resonant ionization mass spectrometry, sometimes called RIMS rather than SNMS, is where you're using a special wavelength of a laser to ionize certain species. And you might have to use two lasers because there might be two transitions you want to get to ionize the species. And then these ions that are produced by post-ionization of the neutrals are then measured. And this reduces the matrix effects in SIMS. So SNMS is more quantitative. It's less dependent on the chemistry. And that's one of the reasons that people develop the SNMS procedure and sell these instruments to reduce these so-called matrix effects in the material. So here's an example of comparing SIMS with SNMS. Up the top here, this is a positive secondary ion spectrum from gallium arsenide, okay? And down the bottom is the SNMS. So SIMS versus SNMS. They've both got logarithmic scales. But if you look at the spectrum, let's have a look. So in the top one here, here's gallium. Okay, this is gallium arsenide. This is logarithmic. So you can see gallium in different species, different mass to charge ratios. Here's gallium. Here's arsenic. So you can see the biggest arsenic peak is what? 10, 100, 500 times smaller in the positive SIMS spectrum than gallium. Now, the negative SIMS spectrum is going to enhance the arsenic. But in this spectrum, you can see the signal from the arsenic is about 500 times smaller than from gallium. even though you have equal numbers of gallium and arsenic atoms in the material. And this is, I mentioned, about the problem of quantitative analysis. But when you use the sputtered neutral mass spectrometry, and this is an example using electron impact to ionize the species. This is the SNMS spectrum. And you can see now the heights here of the gallium and arsenic peaks are very close together because you ionize these neutrals and you're going to have equal numbers of gallium and arsenic coming off pretty well. So when you ionize these, you're going to get essentially equal numbers of them. So it reduces these matrix effects in the looking at the neutrals coming off. So post-ionization is an approach to reduce these so-called matrix effects. The resonant ionization, we're using a laser here for looking at certain species, is also extremely useful. This happens to show a time of flight detector where you're timing the flight of the species coming off down to the detector. So you're ionizing the neutrals, this blue region here of the neutrals, with a laser. So you're using pulsed ions. The ion beam is pulsed, so you get these neutrals coming off. And when the neutrals come off, you hit them with a laser. The laser is also pulsed to produce this resonant ionization. And in time of flight, you must use pulsing also, even in SIMS, static SIMS. If you have a time of flight analyzer, you must pulse the ion beam and measure the times after the pulse that removes the species. This the laser ionization approach can be used for studying many elements. And this is just a periodic table of using laser ionization published recently. It shows you here in blue are the species that have been published using this resonant ionization. And the ones in red would also be accessible using this laser combinations and so forth. And the green ones show you where they've actually used isotopic measurements, learn something about the isotopes. So by studying isotopes, you can learn something also about materials. There's some interesting research areas that rely upon isotopes. I'll just give you a couple of examples. This is a sputtered neutral mass spectrum of a tumor sample using a gallium ion beam. Gallium is a liquid ion beam that they use, and forming maps of certain species here from a tumor, different species, and by scanning the beam across the surface, you can form these images of the different chemical species that you get. And this was done here, this work was done at the Naval Medical Research Institute and published in this paper, if you want to read more about that kind of an application in studying tumors. Also, it's used in the for studying stardust and things like that, looking at isotopes in stardust. Okay, on Earth, we often do things like carbon dating and so forth with species that we have on Earth. But in stardust, we have also things like ruthenium. So here's a stardust particle over here, an SEM image of stardust. And using the lasers to ionize the ruthenium, using two different lasers to ionize the ruthenium, and over here compared to what you would get from terrestrial ruthenium. In other words, ruthenium metal here on Earth. And this is the spectrum you get from the stardust. It's very different. So different isotopes, different intensities. So this relates to different things in astrophysics and so forth. But I just want to include that also and give you a reference to that, just to show you the versatility of these kinds of applications of SIMS that we can do. So in SIMS, we have these, looking at the secondary ions, we can look at the positive ions, we can look at the negative ions. We can also look at the neutrals. We can ionize the neutrals different ways, electrons, plasmas, and lasers. We can then do these different types of studies. So lots of different aspects of looking at the secondary ions coming off materials. Lots of different instruments that you have available for use for purchasing. So if you're going to work in this particular field, you want to make sure if you're buying an instrument, you buy the right one. Static SIMS, dynamic SIMS, different kinds of detectors, lots of different things happening with SIMS instruments. And over the years, SIMS has developed enormously. And today we have fantastic instruments for doing SIMS work. Okay. So now I'm going to move on and just talk a little bit about this technique called Rutherford backscattering spectroscopy, or RBS. Rutherford backscattering spectroscopy. So Rutherford found that the nuclei can backscatter ions. So an ion coming into a sample has a probability of being scattered. This is basically an ion species that comes in, and eventually it might interact with a nucleus and scatter. And it might, what we call backscatter. In other words, it comes back towards the incoming beam. So it's called backscattering because of that. We're not looking at forward scattering, we're looking at backscattering. So the species comes in, and we're looking at that same species that comes out. So we use a very high energy ion in Rutherford backscattering spectrometry. We typically use a helium ion of very high energy, 2 million electron volts, very high energy. And some of these ions backscatter from nuclei in the sample. And that's illustrated here. Here's our projectile, mass M1. It has a velocity and a certain energy. And it goes into a material. Here's our atom in the material, mass M2. And it might interact with that particular mass and backscatter. So this is the same species that came in, M1, but it will backscatter. And after it backscatters, it will have a different velocity and a different energy. And it depends upon the backscattering angle, as well as the mass of the species here. And this species here also is going to recoil somewhat in the material, but it will stay in the material, but it's going to take up some of the energy. Okay, so it's also going to absorb some of the energy. And the backscattering angle is this large angle, not this small angle. The backscattering angle is the change in direction of the ion beam in the measurement. So again, you use conservation of energy and momentum. You can calculate out the what's going to happen for the energy of the backscattered ion based on this mass of the species. So this is a technique that doesn't need standards. It can all be calculated out from physics, what the energy would be based on depth in material and the species. So when you have a solid and this energetic ion penetrates into the solid, it's going to slow down by interaction with the electrons in the material. And when it undergoes an interaction with an atom, the energy it has when it gets to that depth in the material where it scatters is going to be less than what it had to start. But then it's going to scatter, and then it has to also come back out through the material and slow down once again. So if the atom's present near the surface, it's going to come back at a certain energy. But if it comes back from a certain depth in the sample, it's going to lose energy. So what we're doing is looking at the spectrum of the energies of the ions coming back after certain scattering. So here's a thought experiment, looking at the energy of the backscattered ions at a specific backscattering angle. Here, 170 degrees is the backscattering angle. About what happens to the energy of these ions. So this is an example of 1,000 angstrom thick gold film. And so a helium beam, energy 2 million electron volts coming in. So at the surface of this gold film, the ions come back at an energy of 1845. Okay. 1,000 volt, 1.845 megavolts. Okay. And that's from the surface. Now, the scattering can occur at any depth. And the maximum depth here at 1,000, when the ions get down to this maximum depth here, they're going to lose some energy in going through this film. And they'll backscatter from the gold atoms at the back. And they're also going to lose energy as they come back through the material. So if they go through 1,000 angstroms of gold and come out from the back, their energy then is 1.712 million electron volts. So this thickness of the film is going to change the energy by 133,000 electron volts. So you're going to see in a spectrum a range of energies of 133,000 electron volts for that kind of a gold film. Species scattered off the surface, species scattered off the back. So this illustrates what you would get. Beam coming in, certain energy. The species backscatter off the surface. This K is called the kinematic factor. This gives you the energy. So the kinematic factor times the beam energy tells you the energy you would get from the species that are scattered off the surface. The ions that go in lose energy, and at the back they're going to have a lower energy. They'll also be scattered by the same kinematic factor, but then they're going to lose energy again coming through the material and come out with different energy. And this is the kind of spectrum you would get. So in the previous example, I talked about the different range, 133,000 electron volts. That would be the range across here of that gold film. So this represents the surface, and this represents the back. So this is depth. You'll also see that the yield is not flat topped. It basically, the signal's increasing a little bit as you go through the film. And that's because the yield changes. Okay. So in RBS, you're always going to see this slightly increasing yield, okay, with the depth. So they're not quite flat topped. They have this slope on them as well. And that's all described here, what I just said, okay, about that. So if you have multiple films or multiple elements, you can estimate the kind of spectrum you get. So here's an example of an alloy of two different species, an element M, capital M, and an element small m. This would just be a simple alloy of two metals, for example, or two materials. And the mass of element M is greater than the mass of small m. So big M is heavier than small m. But the concentrations are identical. So this is an alloy of equal numbers of atoms. So here's the alloy. Okay, this is the atomic concentration and the same thickness. But the RBS spectrum is going to be like this. You're going to have two of these type regions of different energy loss, depending upon the species. So the heavier the mass, the higher the energy of the scattered species. So this particular distribution here represents the heavier element in the alloy. It's going to come back at a higher energy than the lighter element. So this represents the signal from the lighter element. Also, we mentioned we have equal numbers of atoms. And you can see the cross-section is higher for the heavier masses. So the signals you get from higher mass species in a sample are bigger than you would get from a lighter element. So this is a film of an alloy of these two species. Okay. Now, if I had a thick alloy of these two atoms, shown here, rather than just a certain thickness, but now it basically continues down to a great depth, the spectra, this is going to be the same as before, the front, this is the surface of the heavier element. This is going to be the same place for the surface of the lighter element here, but this is going to be thicker now. So this range here is going to increase all the way down because it's a thick film. So this is the signal you would get from that heavy element. The light element starts here at the surface and it's going to continue down also and superimposed on this other one. So when you have a thick film, you're going to have these interactions between the different masses based on the thickness of your film. Here's an example of RBS. It's a silicon sample and it has about 1 monolayer coverage of copper, silver, and gold on it. And this is the spectrum that you get from the energy of the backscattered species. Gold, silver, and copper are all at the surface, about 1 monolayer. And you can see the signals here. This is gold, silver, and copper. And this is ×5 compared to the silicon signal. And I want to point out again, as I mentioned, the heavier elements give you a higher signal. Gold, silver, and copper. But these can all be calculated from physics. So you can verify the concentrations based on the intensities of these peaks. Here's silicon. The RBS, since you're looking at the masses, you can also have the possibility of seeing different isotopes as well, depending upon your resolution. But you can detect a monolayer, okay, with RBS. Here's an example of silicon dope with arsenic. Here's our silicon again. It has arsenic implanted in it. Arsenic is heavier than silicon, so it's going to appear over here at higher energies. And this is the signal measured from the arsenic. Illustrated over here again, amplified. And also the energy converted to depth. And also the signal intensity converted to concentration. So here's the depth distribution of arsenic. These are thousands of angstrom units that you get without sputtering. It's basically looking at the species in a sample without sputtering. So it's a non-destructive technique in terms of composition to do depth profiling. So it's easy to detect heavy elements in a light matrix. It's much harder to detect a light element, a heavy matrix, because the signal from the lighter elements is going to be superimposed on a background from the heavier elements. But one nice thing about RBS is that you can actually do experiments with, like, for annealing, for example, and look at changes in chemistry with annealing. And this is an example of that. This is a molybdenum film on silicon. It's also got a silicon coverage on here on the top to protect the sample. So all these spectra are taken on the same place on the sample. And what you're looking at here is molybdenum on top of silicon with this protective silicon layer and heating it with a laser to form a silicide of molybdenum. So before heating it all, this is the RBS spectrum here, the solid line. This is the solid line here. This is the spectrum of molybdenum, this solid line. The silicon, this is the silicon spectrum. Okay, and this represents this silicon surface here below the molybdenum. But you'll notice also this little bump here, and that represents this silicon protective layer on top of the molybdenum. And when you hit it with a laser, 6 scans with a laser and so forth, you see that the molybdenum signal is decreasing and it's becoming broader. This means the molybdenum is going deeper into the material. The surface still has more molybdenum than deeper down. And conversely, the silicon, okay, is also coming up towards the surface. So you're forming this molybdenum silicide. So now the silicon that's buried down deeper is decreasing, and the silicon signal up near the surface, which was here, is now also increasing. And after 12 scans with a laser, you form the molybdenum silicide to a certain depth. So here's your molybdenum silicide, and you're going to have silicon below that has not been formed into a silicide, and this signal here is going to be from your silicide. So you can do experiments like this, okay, without sputtering. You can follow reactions in RBS, formations of these kinds of things with time. So RBS is a very useful technique. And another example here, showing you arsenic diffusion. Here's a titanium layer. Here's a bulk silicon layer. Here's the surface layer of silicon. And here's your titanium and arsenic. So this is before any kind of treatment. And this arsenic peak is enhanced 30 times to make it bigger. Over here is after heating it for an hour at 500 degrees Celsius. And you can see now the arsenic is changing. We still have arsenic at the surface, but some has diffused into the material. And when you heat it to a higher temperature, we have a very complex spectrum because of what's happened. So here's our arsenic. This is titanium. And this is silicon. So again, okay, you can see the RBS gives information about where the elements are. And the titanium here is now overlapping with the silicon, and that gives you this bump. So the interpretation of RBS spectra can be complex, but you really want to know the species that you have in your sample. But once you know the species, you know what to expect, and you can determine the thicknesses, where those elements are with RBS. So in RBS, we need this high energy beam. Here's our target and our detector. In this particular figure, this is not good because it implies this backscattering angle, and it's not. Okay, the backscattering angle is the change in direction of your ion beam. So the backscattering angle is a large angle. It's not this small angle. So here's a summary of RBS. Okay. You can detect beryllium and heavier elements. The detection limit is about 0.1 to 10 atomic percent. It may not be as good as Auger spectroscopy and XPS, certainly not as good as SIMS, but it's better for heavier elements, particularly on light substrate. But it's quantitative without standards. You can calculate out the composition without standards. The depth resolution is about 10 nanometers. The analysis diameter is typically about a millimeter, and the analysis depth is about a micrometer. And we don't do imaging with it. Okay, it's a very nice technique. There aren't that many RBS instruments around the world compared to other type instruments, but they can be very useful depending upon your need. So it's very important to understand some of the principles and properties of the backscattering spectroscopy. Okay. So that basically is a summary about the different ion techniques. Ion scattering spectroscopy, extremely surface sensitive. SIMS, positive and negative spectra. Lots of different approaches, time of flight analyzers, magnetic sector analyzers. Static SIMS for studying the surface, dynamic SIMS for depth profiling. Ionizing the neutrals to reduce the so-called matrix effects, to get signals that represent more of the composition. Electrons, plasmas, and lasers to do this post-ionization. RBS, a very high energy beam, okay, of helium that we're using to backscatter, and we can do experiments down to a certain depth and look at diffusion and so forth in situ with this particular technique. Okay, they've all got different properties. It's important to realize these different properties and know which one you might want to use in your research. So if you're making films or you're making coatings, improving wear resistance, things like that, once you know what you want to learn, then you select the technique to give you the answer. Okay, and that's why I've tried to illustrate some of these different techniques. Now I'm going to finish up by just talking about a few other, which I don't use. Oh, this is a summary table of the relative capabilities of some of the electron and ion spectroscopies. The range of detection is a very specific range and sensitivity factors, detection limits, spatial resolution, depth resolution, and so forth. Advantages, disadvantages between these the different techniques. Okay, I'm not going to read over those, but you have that in your notes or in your PDF copy that you can compare these different techniques. So it's a summary of these different techniques: Auger spectroscopy, XPS, ion scattering, SIMS, and RBS. Now, some of you use X-ray fluorescence to determine the compositions of your materials. It's a very common technique to determine the composition of your materials. It's an excellent technique. And but there's another aspect of it that you can also use: total reflection X-ray fluorescence. So it's a different aspect of X-ray fluorescence. So If you're doing just simple XRF, often you can do it by handheld machine and so forth. But total reflection XPS is a much larger instrument. So it's a surface instrument for looking at the tracer elements, particularly of particles on the surfaces of smooth surfaces, particularly in the semiconductor industry, where you have maybe particles, which I showed you some examples using Auger spectroscopy. We identify the composition of these particles. But total reflection X-ray fluorescence is used for looking at deposits on smooth surfaces. So the X-rays are basically coming in at a very glancing angle. And the angle of incidence, they're saying here, is 0.05 to 5.5 degrees, the incident angle. Well, this is the angle of the beam in relation to the surface. Okay, so it's not really the angle of incidence, it's that angle between the beam and the surface plane. It's a very low angle, half a degree, okay, and even smaller than that. So what you're trying to do is have the X-ray beam come in, but not penetrate into your sample. Now, it will penetrate in to some extent, but you're trying to bring it in to enhance the signal from any species that is on the surface, contaminant on the surface of a flat surface. So the glancing angle of the X-rays limits the excitation to about the top 8 nanometers, depending upon the material. So it's a surface analysis, it's not a bulk analysis. And we're looking at the fluorescent X-ray signal coming from the sample. And we're trying to identify the contaminants that are present on the surface. This illustrates the principle of it. Now, this angle here, as I mentioned, is quite small, much smaller than shown here in this schematic. Okay, 0.1 degree would be basically lined up with the surface. So it just, for illustrative purposes, shows you the incoming beam, but this angle is extremely small. And this is the reflected beam of the surface. And here, for example, is a contaminant on the surface. So the X-rays come in, and you're looking at the fluorescence, the signals coming out here from this these contaminants on the surface with our detector. And up here in the top right, it just illustrates what would be happening with incident angle. So at low angles of incidence, we're basically measuring the composition of these deposits. If the angle of incidence becomes greater than this angle here becomes greater than the critical angle, we're going to be looking down into the bulk of the material. Comparison here, X-ray fluorescence and the total reflection X-ray fluorescence, where now we're looking again the very small angle between the X-ray beam and the flat surface, and looking at the radiation coming off of these deposits here on the surface. This is the kind of spectrum you get with the total reflection versus what you would get from conventional XRF. So you're basically getting a signal here from these contaminant particles on the surface. This is just a slide I took from a recent publication to show you basically here a multi-element pattern solution, showing you sort of detection from all these different kinds of species here. So these are the energies of the X-rays you're detecting here from using a molybdenum X-ray beam. Okay, so it gives you an idea here of the elements. So the mass deposit for each element is about 10 nanograms in here. Okay. Okay. This is contaminants on a silicon wafer. This is where the technique is often used in the semiconductor industry to identify particles on wafers. And you can see here, in this particular case here, many elements detected from this, these metallic impurities on a silicon wafer. So you're looking at the fluorescent X-rays coming, but basically you're looking for elements from sodium up, detection limit, depth resolution. Again, looking at this near the surface. Okay, you can do imaging mapping by moving your sample around, and then the lateral resolution is going to depend on probe size, which is about 10 millimeters. So that's just a brief introduction to TXRM. Okay, just so you know about that technique. And like I said, it's normally used in the semiconductor industry for looking at surface contaminants. Just now, a couple of few slides about scanning probes. And in the back of the notes, there are articles about these scanning probes in more detail. So the two common scanning probes that we use are scanning tunneling microscopy, STM. And this is only useful for conducting materials because they're scanning and looking at electrons that tunnel from a sharp tip, between the sharp tip in your sample. So they have to be conductive. It measures that current between the tip and the specimen. And this was the STM that was developed, I mentioned it the other day, by people at IBM who weren't supposed to be doing it. Of course, the company said it won't work, but they ended up getting a Nobel Prize for it. Binning and Roy. But then people thought, I'd like to study non-conducting materials. So how can you study non-conducting materials? Well, that's called the atomic force microscope, AFM. You can also study conductors with it. And so it applies to all materials. And you can measure things, for example, the electrostatic force between the tip and the specimen. And there are different types, subtypes of this AFM. You can have a contact AFM, where you're scanning the tip in relation to the sample. You can also have non-contact AFM, where you're looking at a force between the tip and the surface. Okay, and you have different modes also. Tapping modes of atomic force microscopy. There are many modes of atomic force microscopy. You can also have magnetic force microscopy by using special tips as well. So over the years, the simple AFM has been changed into all kinds of different ways for studying surface properties. So this illustrates a scanning tunneling microscope. You have a sample. Okay, you put a voltage here between the sample and the tip. And you can move the tip around by piezoelectric crystals across the surface. And this region here is expanded up schematically here, showing you atoms. So you have the atoms here in the sample. And up here, these are the atoms in your tip. So you're looking at the current between your tip and the atoms in the surface. So as you scan the tip across a small region here, when the atoms are close to atoms in the sample, you get tunneling current. And when you are between the atoms, the current is going to decrease. So this current is exponential. It changes rapidly with distance. And the whole idea was, I think people at IBM felt they could never get a tip that had a single atom on the end. Well, it turns out that it's self-correcting. when you have a sharp tip, the atoms that happen to be closest to the end are automatically selected because of the fact that it's exponential behavior. So that was the reason that it really works. You don't need to have a tip that just has one atom at the end. It's going to self-select whichever atom happens to be near the end of your tip. So you can scan this across the surface and see the distribution of the atoms by measuring that current. To me, this is some studies that was done just a few years after the announcement about the technique. And back in the 1960s, there was a lot of work done on silicon-111. The annealed surface of silicon-111 has a very unique structure. The atoms are not present where they would expect it to be. If I take a silicon crystal and cleave it, I will have a 111 surface. But if I anneal that surface, it changes the structure and gives this famous structure, which is called the silicon 7x7 structure. Now, people use electron diffraction, low energy electron diffraction, to predict where the silicon atoms are. What is the surface structure? And several people, like Elmer Gray, came up with, this is not very clear, came up with a certain distribution of where the silicon atoms would be to give you the observed electron diffraction pattern. Okay, and there are several of these different models that were proposed. And down the bottom here is the STM image of silicon 7x7. And this agrees very closely with one of the models that was proposed up here. So somebody had the right answer, but they didn't know which one was right, which model was right, until the STM came out. And to me, it was amazing because I studied the silicon 7x7 structure back in the 1960s. Okay, I didn't do any calculations about where the atoms are, but I was aware of these different models that people had. But once the STM came out, there was an obvious material, obvious surface to study with the STM to see where the atoms are. And I was amazed at it was agreement with one of the models, that somebody actually made the correct prediction of where the atoms are. This is also an interesting aspect of the scanning tunneling microscope. Gallium arsenide. By changing the polarity, you can image either the gallium or the arsenic species. So gallium arsenide is a very important semiconductor, but the gallium is positive and the arsenic is negative. So you can actually detect the different species, the fact that one's positive and one's negative, by changing the polarity between your tip and your sample. So over here, these are the two STM images that you get with different sample voltage, positive voltage and a negative voltage. And over here, on these two images, you can see what's going on. Down here, so where oxygen, these atoms here that are circles, and the black represent the gallium and the arsenic atoms. So the arsenic atoms are represented by the open circles, and the gallium atoms are represented by the closed circles. And this is a certain orientation of gallium arsenide. And here are the two STM images by changing the polarity. This is the so-called unit cell. This is the smallest repeating unit that you have. So in this particular case, A, okay, you image one of the species. And if you look down here, you can see that what you're imaging are the black circles here, and the black circles are the gallium. So this particular STM image is imaging the gallium. You see? But in between here, we have arsenic atoms. And the arsenic atoms aren't being seen. But when you change the polarity, you will then see the current tunneling between the arsenic atoms and the tip instead of the gallium. So if you look over here in this same rectangle, you're now imaging here the arsenic. So you can image the gallium and the arsenic separately with the STM. And to me, this is also a very beautiful way for looking at the gallium and arsenic distributions on different surfaces of gallium arsenide. The atomic force microscope can be used to look at any material. And illustrated over here, excuse me. This is the sample surface here shown in green. This is a tip on a cantilever. So if you think about it, you just scan this sample across this tip. This tip's going to move up and down. And this up and down motion can be detected by using a laser and a photodiode up here to measure this motion. So you can measure the topography of the sample. Would be one where it's in contact, for example, across this green material, and measure the topography on an atomic scale. And is an example of the tip of a cantilever, different designs of these tips. And this just shows you a variety of probes that you can buy for doing atomic force microscopy measurements. They've designed tips specifically for different purposes. They've got different shaped tips. There's some that are like this high aspect ratio, like needles, and so forth, depending upon what you want to use. And they're doing different measurements, atomic force microscopes. You can use magnetic properties, all kinds of different things. You have all kinds of different tips. Here's an example again of the silicon 111 7x7 surface structure. And this was measured with an atomic force microscope rather than the STM, showing you different scan speeds, 400 milliseconds per line and 50 milliseconds per line. You can see at the high scan rate, the image is not as good as you have when you're scanning more slowly. So you can also see that where the atoms are on the surface of silicon with the atomic force microscope, as well as the scanning tunneling microscope. This is also an interesting case. On the silicon surface, 7x7 structure, you can see here the 7x7 structure. It doesn't show up as clearly as I showed you earlier, but this is a step, atomic step on a surface. So this is a single atomic step. So the vertical resolution is very high, 0.02 nanometers. So this just shows you the case where you can image steps on a surface. So just a few slides, finish up. I just want to talk about, I mentioned some reference materials. You saw some reference materials for doing imaging and so forth. And you can have reference materials for calibrating your OJ maps or SEMs, for example, and these can be traced to the national labs. So Gallup Microanalytical sells different kinds of reference standards to calibrate and check out your resolution for OJ spectroscopy and also for X-ray photoelectron spectroscopy. It also uses them for SEM. The people in Germany have developed a lateral resolution using semiconductors for very high resolution, which is also used for OJ spectroscopy and for SIMS. And there are also sputter depth profiling standards of different materials to calibrate your sputtering rate based on these different materials. Also sold by Gallup, Microanalytical Lab. Documentary standards. There are many standards in surface analysis produced by ASTM International. Okay. It used to be just called the American Society for Testing and Materials, but now they've called themselves ASTM International. And also ISO, International Organization for Standardization. These are sold by these organizations, basically standard procedures for surface analysis. ASTM has a committee, E42, on surface analysis, and I chaired that committee on OJ spectroscopy for many years and been involved with them over the years in developing a lot of these standards. And they have 22 published standards, and they had many others, but they've been withdrawn because ISO took over those documents and they made them international standards. And similar people that work on ASTM also work on the ISO technical committees. So they made them from ASTM standards into ISO standards. And in surface analysis, we have a committee, ISO Technical Committee 201, on surface chemical analysis. And this committee has published 73 standards on surface analysis. So there's two more slides to finish up. This is from Evans Analytical Group. This slide's been around for a long time. I don't necessarily agree with it 100%, but it gives you a good illustration. So this is the spatial resolution down here. And this is the detection range. So this is the atomic percent here. As you can detect, parts per billion down here, 1 part per billion. Okay. But of course, it depends upon the size of your beam, the time, and so forth. But it's a general comparison of techniques. So let's look at some of the techniques that we talked about. OJ electron spectroscopy, we talked about it. So it represents this particular region here. We can go down, excuse me, in that chart, down here to something like 10 nanometers, which I mentioned is about the spatial limit of OJ spectroscopy. And the detection limit, about 0.1 atomic percent. See? Kind of limit. XPS or ESTER over here. We don't have the spatial resolution that we have in OJ spectroscopy. In their particular figure here, they're showing about 10 micrometers. Well, a lot of the instruments today, we can get down closer to 1 micrometer. But again, the detection limit, about the same as OJ spectroscopy, about 0.1 to 1 atomic percent. So this is the XPS or ESTER that we talked about. And they've also got in here RBS, the backscattering spectrometry, spatial resolution about 1 millimeter. Okay, we can detect lower concentrations, particularly for heavier elements. Maybe down to 10 parts per million for heavy elements in using RBS. Total reflection XRF. Okay, the beam size is bigger, order of several millimeters. We have the capability, though, of detecting also low concentration with this technique. And if we look in here, this is XRF. See XRF? We can look at smaller areas, but we don't have necessarily also the same sensitivity. We compare some of the Auger work with EDS, and over here it shows you different aspects of EDS. Well, that's the using a TEM, that's really going to be very good. Let's see, here's the SEM EDS here. You see, we don't have the spatial resolution because of the electron beam spreading out and giving this inverted balloon. And also we don't have necessarily the same sensitivity because of the background that we have also in EDS spectra. TOF SIMS, we're looking at the top atomic layer. We can have well-focused ion beams, and we can detect down here parts per billion. And dynamic SIMS, where you're sputtering, is shown down here with extremely high sensitivity, the highest sensitivity of any of the techniques that we have for looking at species. And over here, atom probes, looking down to atomic levels and so forth. So this compares a lot of the different techniques that are used for studying materials. And the last slide is just another one from Evans' analytical group, presented a different way. And it's hard to read these, so I just labeled them for some of the things that we use. This is 3 nanometers, 10 nanometers. So the orange goes down 3 nanometers, is 10 nanometers, 100 nanometers. So the atomic force microscope is just looking right near the surface, you see. Time of flight SIMS is looking at the surface. But you can sputter away layers and look further down. This represents sort of depth profiling. Auger electron spectroscopy is looking down something like 10 nanometers. But you can sputter though to go down to something like a micrometer. XPS, similar depth of analysis, but again, by sputtering, you can also go down to something like a micrometer. This is the TXRF, looking down to perhaps close to 10 nanometers. RBS, looking down here to about a micrometer in depth. EDS, also looking down to about a micrometer in depth. But SIMS, where we are stuttering away material, can go down to great depths down here as well. Okay. And this is the static SIMS, normally time of flight SIMS, static SIMS, and this is the dynamic SIMS. This is what they call, how they label theirs. I would prefer to label this not TOF SIMS, but static SIMS, and this one over here as dynamic SIMS. So it also shows you some other techniques that we did not talk about. But this is another chart from the Evans analytical group that gives you an idea about the different techniques. So I think almost perfect timing, isn't it? So this completes the my part of the course, and I hope I've explained all these different techniques to you in a way that you understand some of the principles, that you know about them, that you can refer back to the notes to help you select a technique when you want to look at a certain type of material, surface material in particular, a coating or production or making coatings or films and things like that, to analyze them, to get the best information you can to help you in your research or in your development or in your manufacturing and so forth. good samples, bad samples, something's goes wrong, you might be able to use one of these techniques to find out what happened in a growth process. Okay, so thank you very much. As you can probably tell, I enjoy teaching, and I just appreciate the fact that you invited me here. I was here in 2010 and investigated a course over there as well. And my second visit to Pakistan, I told my family that the Pakistanis are perhaps the most hospitable people in the world. They look after you, they treat you like royalty. I mean, I told them that last time I was here, they put on a show and they sit you in these big armchairs in the front row. Well, last night, guess what? They sat me in the front row again. Okay? I mean, talk about treatment. I mean, thank you so much for your hospitality. I really appreciate it.
Thank you. It was a really great opportunity actually to attend your lectures, and we witnessed new insights to the grasp of these specific techniques. So I hope that it added a very comprehensive knowledge for the separate techniques to all of us. So thank you very much, sir, once again.
Thank you.
So now we'll have a break for lunch, and you are requested to be here exactly at 2:30 that we can start the closing ceremony. So see you back at 2:30.
applied surface science are vast and ever evolving. Your journey does not end here. It is only the beginning of our lifelong knowledge and excellence. The path forward is paved with opportunities, and I encourage each of you to seize these opportunities to apply what you have learned and to continue to push the boundaries of knowledge and innovation in vacuum applications. This event could not be possible without the support of our sponsors. We acknowledge and appreciate our following sponsors, organizations, and companies to organize this event: Pakistan Science Foundation, Islamabad; MS Al Kartas; Messrs Imtiaz Cabinet, Islamabad; Nestec; NR Petrotech Refinery Facility, Karachi; International Vacuum Center, Islamabad; Kunche Sialkot; and People Steel Mill, Karachi. Thank you for being part of this course, and I wish you all the very best in your future endeavors. Safe travels, and may your paths be filled with discovery and achievements. Thank you.
For your kind words. So during this course, we have a very interactive sessions, but I think the course outcome cannot be completed without the feedback from the participants. So I will invite two participants for their feedback. It will help us for improvement and the future programs. So first of all, I will request Dr. Noor Asnida from Malaysia for his comments about the course.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Allahumma salli ala Sayyidina Muhammad wa ala ali Muhammad. I must say that there's a little bit of correction. I am Dr. Atika. I'll be sharing my thoughts about the program for the last 3 days. So I'm actually coming from Malaysia and servicing University Technology Mara as the associate professor in the School of Chemical Engineering. And to be honest, I didn't imagine that I'm going to be here for this particular program because my visa was in process not until less than 24 hours before the departure. So I must be very grateful to Allah subhanahu wa ta'ala given the opportunity for me to be in Pakistan for the first time. It wouldn't be fair if I didn't extend my appreciation to the Pakistan Vacuum Society and as well as IOC comstech for inviting us from Malaysia to be here. We are very grateful to be with experts as well as colleagues, coming from various backgrounds, which having the same interest. And the last 3 days of the training has been very fruitful. It's well organized, and particularly we'll be able to listen to inputs from industries, which obviously give us some added information. And the gist of the workshop itself coming from our dear Prof. Grant, which elaborated comprehensively on the options of material characterization. Thank you so much, Prof. Grant. And on a lighter note, I guess who wouldn't imagine that this workshop will bring us to our long last acquaintance back in Australia. Thank you for solving the puzzle. I find that this training is very useful for my career development as a researcher, as well as my future plan in looking into hydrogen storage. And I would support that this type of activity should be conducted more often. And in fact, I find that it would be fantastic if the Pakistan Society, Vacuum Society, extended this kind of training outside of Pakistan. so that we can actually reach out to more our OIC members, obviously for the better of the Ummah. And once again, I would like to extend my appreciation to the host who had actually organized the program very well. Thank you so much. And I look forward to be back to Pakistan again. Thank you so much.
Very much, Dr. Noor, for your comments. So now I will request Dr. Fajar Mulaya from Indonesia.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Fajar Mulia. I'm from Indonesia. I'm serving as a lecturer in Nanotechnology Engineering Department, Universitas Airlangga, Surabaya, Indonesia. I'm thankful to the Pakistan Vacuum Society and OIC Comstech by providing this opportunity to attend the 29 International Technical Training course on vacuum application and applied surface science being held here at OIC Comstech. 3 days training course was very well organized. Thank you so much. And all the research person present their talks in professional way. We meet from academia, also from industry, so we can make connection each other. Thank you so much. And also I would like to thanks to Professor Grant. Thank you so much, Professor, who gave us detailed talks during the 3 days on characterization techniques of the materials. This training is very useful to my field, especially in nanotechnology engineering. So I can bring the knowledge from here and apply it in my university, and I will teach to my student, and also it will be implemented in my research. With the support of OIC Comstech, I recommend Pakistan Vacuum Society such type of training course related to vacuum application within and outside Pakistan, maybe in Indonesia next time, hopefully, as well also to benefit the other OIC Comstech member countries. Once again, I appreciate the joint effort of Pakistan Vacuum Society and Comstech for organizing the current training course. And this is the first time I visit Pakistan, especially Islamabad. Thank you so much for your kind hospitality. I'm so happy to be here. Thank you so much. Maybe we can meet next day and maybe in Indonesia. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Now I will request Dr. Muhammad Iqbal from China for your comments.
Assalamu alaikum. Actually, presently I'm working in China, but I belongs to Pakistan. So my name is Dr. Munawwar Iqbal. So as I told that, actually China is going to build the largest, biggest laboratory on earth. You know, the Large Hadron Collider, it is a 27-kilometer circumference laboratory, but now China has planned to build 100-kilometer circumference laboratory in China, in Beijing. So I am part of that machine. So actually this course is very useful for me, you know, on accelerator, on every part of accelerator, the vacuum technology, science and technology is important and essential part of that technology. So this course was very important for this, and I am also grateful for the Pakistan Vacuum Society and Comstech to invite me here and to be a part of this wonderful event for this training. And it's a great opportunity for the student and the expert working in the field of vacuum science and technology, particularly in the material science and engineering. As far as the resource person of the training is concerned, so Professor Grant is itself is the authority on this surface science and technology. I'm grateful, sir. And you have conducted this training. I think it was useful for all, especially for the student and for the expert in the field of vacuum science and technology. I appreciate your capabilities and above all, your energy, the way you conducted. It looks that you have a great energy. So I appreciate it. I wish you a healthy life to come so that the young generation can get more benefit out of your expertise. And finally, I would say the Vacuum Society is a very good, important platform for young student and also for the expert. And its events should be extended frequently, not only inside Pakistan, but also outside of Pakistan, because this is a very fundamental kind of technology. Without vacuum, so no technology, as far I know, there is no technology can exist without this technology. So thanks for the organizer again, for the organizing and the resource person again. Thank you very much.
Very much, sir. And finally, we have one more comment from Dr. Muhammad Sabtan Abbas from GC University, Lahore.
Assalamu alaikum, everyone. On behalf of the participants, I express my sincere gratitude to the organizers, Pakistan Vacuum Society, and also the comstech. Actually, most of the things have already been mentioned by the other participants, but one important factor which I have observed, that is the energy of the resource person. I mean, he was full of energy even at this young age. So thank you so much for organizing this informative training session. And I wish this kind of event should continue, not only in Pakistan, but outside Pakistan, using the platform of comstech. So thank you so much.
So during this training course, we were honored to have the presence of Professor John T. Grant with us. Actually, already mentioned by the participants, he solely conducted the 3-day training workshop, although we filled some slots by the other presenters, but he was the only person who conducted this workshop for the 3 days. Dr. Grant has extensive experience in the field of surface science, having worked in this area for over 4 decades. So now I will request Dr. Grant for his experience and suggestions for some future programs in here. So please.
Well, I didn't prepare a speech. I didn't think I was going to be giving one. But Excellencies, honored guests, this is my second time in Pakistan. And this time I didn't have a problem with the visa. I think I might have beat you because last time I didn't get my visa until like 6 hours before my plane took off. I wasn't sure if I would come. So this time, no problem. Maybe they have my name somewhere back in a file. But anyway, I came here the first time in 2010 when I was a guest at Invest, also where I gave a talk, and really enjoyed that. And I told people I've been ill this year. Some of you know that. And I just finished some treatment recently, and a lot of my colleagues said I should not go because of my health. But I knew a lot of people depended on my coming, and I decided I would come because I felt pretty good. And I really enjoyed teaching to pass on my knowledge to the other generations, because they're the future of science and technology. And I feel extremely important. So I decided to go against a lot of wishes of people and come to give this special technical training course. And I've thoroughly enjoyed my time here. I told my colleagues that when you come to Pakistan, you're treated like royalty. I told them, like last time I was here in 2010, we had a concert also. And here I was sitting in the front row in these big armchairs, enjoying things. And last night, the same thing. Here I was sitting in the front row, just enjoying things. You treat your guests so well. And I think of all the places I go, I think Pakistan is the most hospitable to guests. I've never had my photograph taken so many times with attendees of the training course. Okay, it's just wonderful to have so many people come up and want their photograph with me. And that, I think, is absolutely showing an honor that I really appreciate from everybody. It makes my stay here again so enjoyable. And I just want to thank everybody, those that invited me, the Pakistan Vacuum Society, Comstech, and Vista, for also providing some funding for my travel here to come and give this course. So I just want to thank everybody for, I'm just amazed how many people came actually, and how many people came online. And I met so many nice people. So I've really enjoyed my stay here. I'm going to be going back to the United States. I'm originally from Australia. That's why maybe you think I don't have an American accent, and you're very correct. I'm Australian, but I spent most of my career in the United States. And I have a really fun time in my career. I really enjoyed my research. And I retired about 9 years ago. And I still remain active. I still read the literature. I still keep up with manufacturers of equipment and read the literature, enjoy going to conferences, giving courses, and so forth. It keeps me active. And my doctor says, keep active. It's very important to keep up your activities and knowledge and keep reading. Another thing that I really enjoy is teaching from different levels. Just this last month, well, I did most of my research in Ohio, in the United States. And after retiring, I moved to Florida because one of my daughters is in Florida. I have a daughter also in Ohio and a son in New Mexico. So we have this big triangle, 1,000 miles between each of them. So we travel back and forth, particularly in Ohio. I was just there this month. And when I go to Ohio, I volunteer a lot. I volunteer in the schools. And I was only there for 3 weeks. And I went to 6 different kindergarten classes to teach them about magnets and also about ultraviolet rays. And it makes me so happy to be able to do things like that. I wear a wizard hat, and somebody said it looks like the flag of Pakistan. And I wear a hat because one of the first times I ever volunteered with kindergartners, they came up to me and said, "You don't look like a wizard," because the program is called Wizards of Right. And so I bought myself a wizard hat, which I now wear when I teach the young kids. And I also teach high school students, volunteer, on how to use electron microscopes. So they restarted that program at my research institute where I used to work. And the first time in 3.5 years after COVID, we started up the program again, and I happened to be in Ohio. So the organizer knew I was coming to Ohio, and she said, would you like to be involved? And I said, yes, I'd like to give the talk to explain to the students about how a scanning electron microscope works, and then go down with them and use our scanning electron microscopes. And they are just amazed. They can actually use these very expensive pieces of equipment and increase magnifications and see beyond what they can see with their eyes or what they can see with an optical microscope. And I challenge them to keep increasing magnification because there's more matter, and the higher the resolution, the more you can see. We can't see the atoms, but we can see lots of levels of different magnifications. And I really enjoy that program as well. And I enjoy coming to and give talks about surface analysis. It keeps me active, it keeps me happy. And I really enjoy it. So I just want to thank everybody for coming, enduring the course, and again, the incredible hospitality that everybody has shown me. So thank you very much.
Thank you, sir. Ladies and gentlemen, as you know that this event is organized by Pakistan Vacuum Society. And now I will introduce the man of inspiration for all activities of Pakistan Vacuum Society. I request Patron-in-Chief Pakistan Vacuum Society, Mr. Zahir Ikram, for his valuable words.
Bismillahirrahmanirrahim. Rabbi shrah li sadri, yassir li amri, wahlul 'uqdatan min lisani yafqahu qawli. Honorable Naeem Sahab, former Chairman, Pakistan Atomic Energy Commission. Shahid Mahmood Beg, the guest of honor, Chairman, Pakistan Science Foundation. Professor Dr. John T. Grant, Dr. Javed Ehsan Bhatti, and Chaudhry Tariq Sattar sir. Participants, ladies and gentlemen, Assalamu alaikum. It's an honor for me to speak all of you at this occasion when you are finishing your hectic job. And I'm especially thankful to Professor John for sparing his time to come to Pakistan and giving such a good training sessions that everybody praises him. And one of the participants just said he is a young man. You know why he's young man? Why he's energetic? Because he's a vacuum man. He sucks all the energy from the environment. That's why he is young. And I'm especially thankful to him for his remarks and the remarks of the others about my beloved country. I'm really thankful and grateful that he appreciates our hospitality, our country, our people. It's a great honor for us. I'm really thankful to everybody who is praising my country, because we need these words a lot to be told to the world that we are a peace-loving and hospitable people. I won't take much long before inviting the chief guest here, because I'm also grateful to him that he accepts my request to chair this session. Naeem sir. Whenever I spell out the word vacuum, I feel vacuum. When I talk about the vacuum science, I observe science and the vacuum. Or you can say vacuum in the science. So it is very important that we must organize these kinds of workshops, because without the vacuum, you cannot survive. As Professor Grant just told us that he got his visa for the first time just 10 hours before or 6 hours before his flight, because our vacuum system of embassy was malfunctioning at that time. So it has not been able to pull the paper of his visa. But this time we have taken care of it because we have learned the vacuum and we have learned how to manage the vacuum. Sir, so next time you will not face this kind of I apologize for the last time. And I hope you people have enjoyed this workshop, and you must be taking something with you which you can apply in your fields. And in the next session or in any next course, you will be able to contribute more. Thank you very much.
So now I will invite guest of honor, Mr. Shahid Mahmood Beg, Chairman of Pakistan Science Foundation, for his words.
Thank you. Bismillah Rahman Rahim. Honorable names of Nishan Imtiaz, Star Imtiaz, Hilal Imtiaz, former Chairman, Pakistan Atomic Energy Commission. I have the honor to work under his leadership for 34 years at Atomic Energy Commission. He is still my mentor, and I often take advice from him. Thank you, sir, for being my mentor and my leader. Thank you very much. Professor John Grant, thank you. He visited my office yesterday. I'm sitting just next to this building in Pakistan Science Foundation. I'm very much impressed by the surface science, but the other thing which amazes me and very exciting and inspiring for me, he showed me some pictures of explaining the STEM modules to the kindergarten children, 4 or 5 years old kindergarten children. I was so amazed, so impressed by this gesture. Although I'm impressed by you are a world authority on vacuum science. We want to promote this type of culture in Pakistan. The senior level people of my age and the people sitting on this row and the front row, they should be visiting the schools, primary schools, high schools, and kindergartens to inspire our students, to motivate our students to explain the law of nature, the science. Here we have the culture of memorizing science. So that's why we are not producing the best of the best scientists from Pakistan. We from Pakistan Science Foundation, we have also introduced the STEM program, that is the science, technology, and engineering and mathematics. The project director, Dr. S. Rose, Dr. Adib, Dr. Sakib from PSF, they're also sitting here and they are taking care of this project. We are trying to introduce this STEM program, STEM education, that is learning by doing, not by memorizing. And we are trying to bring a paradigm shift in Pakistan. So our students, our scientists, should know actually what is happening in science. It is not only the memorizing. So thank you very much, Dr. Bhatti Saab, for organizing this wonderful 3 days event. Ladies and gentlemen, there are 36 scientific societies which are registered with Pakistan Science Foundation, and they contact us for financial support and to organize their scientific activities and scientific events. And without exaggeration, I can share with you the Pakistan Vacuum Society is the most dynamic and most vibrant society in Pakistan. Bhatti Saab often calls me, visit my office, discuss about various events they are going to organize, invite me and my team. And we are so happy that they are popularizing the science and promoting the science culture in Pakistan. And this is what we are here today to promote the science, to discuss science, to share our ideas. The people from different expertise are here. So this is a wonderful platform. We are providing an excellent platform to exchange your idea, to establish the networking. You see, now every science is a multidisciplinary science. And not the state-of-the-art lab in the USR, in the developed world, has all the facilities under one roof. You have to establish collaboration, networking to do some good science. So this is the platform, and this is the forum which Dr. Bhatti and his team, Pakistan Vacuum Society, has arranged. I know it takes many months to arrange such a international event. And it is quite evident from the remarks of the visitors and the participants how successful this conference and this scientific has been. So Dr. Bhatti and the Vacuum Society, please keep it up. Pakistan Science Foundation is your partner. Although we don't have very huge amount of funding with us, we have limited resources, but whatever we have, we are open for you. We are always, we will be happy to support you by all means. So, thank you. Thank you very much, everybody, the organizers, the participants, Dr. Grant's views. You have already witnessed how happy and how he enjoyed his stay here. He visited our office. We discussed science with him. But again, I would say the most impressive part of his science was the STEM education, which he is sharing with the kindergarten, with high school, and with the middle school, etc. So I will ask all my senior colleagues to please promote this culture in Pakistan. We should visit the primary school, high school, middle school, maybe on the weekend or whenever you have time. We are busy in so many unnecessary file work and other things. Please spare some time, do visit the school, try to motivate our young students to come into sciences. All our best students, they are going in medicine and in engineering, and the students who choose physical sciences and natural sciences, these are those students who are not able to go into the medical art. So our aim is to encourage our students to go into mathematics, into physics, into chemistry, into biology, etc. So we can also produce best of the best scientists from Pakistan. So thank you very much once again. God bless you all. Stay blessed.
Very much, sir, for your kind words and the supports of Pakistan Science Foundation for the Pakistan Vacuum Society. Now, I am honored to introduce our chief guest, Mr. Mohammad Naeem, ex-chairman, Pakistan Atomic Energy Commission. Graduated in 1968, Mr. Mohammad Naeem has tremendous contribution in the field of chemistry. His exceptional efforts resulted in enhancing technical cooperation with international institutions like International Atomic Energy Agency and CERN. In reward of his valuable contributions, President Islamic Republic of Pakistan conferred upon him the awards of Nishan-e-Imtiaz, Hilal-e-Imtiaz, and Star-e-Imtiaz. So it's my pleasure to invite His Excellency, Mr. Mohammad Naeem, ex-chairman, Pakistan Atomic Energy Commission. Sir, please.
Bismillahirrahmanirrahim. Alhamdulillah, salli ala Rasulillahil Kareem. Respectable Tahir Ikram Sahab, Patron-in-Chief, the Vacuum Society, and guest of honor, Dr. Shahid Mahmood, and Dr. John Grant, the chairman of IUVST, Applied Surface Science Division, Dr. Javed Hassan Bhatti, President PVS, and Chaudhry Tariq Sattar Sahab, and the coordinator of the course, the faculty member, the dear participants, distinguished guests, ladies and gentlemen, Assalamu alaikum, and very good afternoon. It's a pleasure to be here. I'm grateful to Dr. Tariq Ram Sahab to invite me and to give me this opportunity to be with all of you to have the interaction. And above all, to have the first interaction with the Professor Grant. So I'm so impressed with your personality, and I have a deep sense of gratitude that you have come down to Pakistan again, and you have for the quenching the quest of the knowledge of my participants of all these, and for loving Pakistan that much. May Allah give you health and prosperity. Thank you very much. I think we can't overstress for the importance of the vacuum and this vacuum science and the technology, because it is a precursor of so many things around these days. Everything where you have the modern technologies, you are encountering with the high vacuums, and for that matter, such societies and such seminars and training sessions are very important, I think. The first of all, when we were in universities or when we started our career, we have the vacuum pump with the tap, and we have that glass, and we could have that vacuum filtration and vacuum distillation that time. So that was the old time. Then we have these vacuum pumps, and then when we had more of our work, important one, then we had the root and the mechanical and the diff and the other pumps and the cryo, and in between there was turbos, and we had the 1019 torr, and all those technologies were there. But wherever we are having a lot of the contribution from the vacuum. So I think this is a good work which the society is doing, this vacuum society, because you have these able the speakers, the learned ones, and the people who have who are in the need of the knowledge for this matter, and they have to augment their knowledge. And I think this should be continued, what I used to call the Talim-e-Balgha, the adult education, what we call in our language. So that I think the literacy. So this is all that, this is part of that. So we should continue with that. And I think if we have all that, I congratulate all the participants also of this international course, and especially the participants who are the guests to Pakistan from foreign countries, that they have come here, and the organizers, their dedication, enthusiasm, and hard work throughout the 3-day sessions. And your commitment to expanding your knowledge in the field of vacuum applications and applied surface sciences is commendable. I believe that this pursuit of knowledge is not just an investment in yourself, but a contribution to the advancement of science and technology as a whole, wherever you are. So this applied surface science course is manifestation of the core principles of Pakistan Vacuum Society, the exploration of vacuum application and for earnest desire of scientific excellence. The knowledge, when shared and applied, can spark innovation and drive progress. It is testament of the fact that the pursuit of knowledge is a collective endeavor, and knowledge we gain is a shared resource that benefits society as a whole. And the knowledge that doesn't have the barriers, these don't have the frontiers, they should be free for all this knowledge, this transfer of technologies and these knowledges. And we are grateful for your visit, particularly Professor. As I have said earlier, that vacuum technology is the invisible force behind many of the scientific and industrial advancements we witness today. It is the core of semiconductor manufacturing, thin film depositions, surface analysis, surface characterization, and even space exploration. And in nuclear power reactors also, it's very important when you have the better these vacuum pumps, and you have the better vacuums, then you can rate with the same specifications, that you can have more of energy from the reactors. So this is also there. So we in the nuclear industry, we have to work more on that as well. I appreciate the role of the course coordinators and for the speakers for their meticulous services. They have the guiding light, sharing their expertise and nurturing understanding of the participant. Their dedication and passion for teaching have played an instrumental role in making this course a resounding success, as it is told by the participants themselves and Professor Grant himself and other speakers. I'm happy to know that it was not just a theoretical knowledge sharing, but also useful practical demonstrations activities as well. This is very important as well. I think that was a better part which you people have done. I appreciate Pakistan Vacuum Society for their support regarding networking among academics and industrial professionals, which is very important, sir. You're doing, but it's a great work because the academia, the industry, and all these people, they have to be interacted and they must have these strong bonds. They should come to these forums, tell their problems, and you can solve their problems. There are so many things which you can calibrate for them, you can manufacture for them, and you can help them to get it from different places. You know the better sources. So you are doing a great work that way, I think. Then I'm told, as people have told my friends as well, that in this 3-day short course, the OIC comstech International Uniform Vacuum Scientific and Technology Application, IUV, STA, Pakistan Science Foundation, and NINVAST, they all have worked tirelessly behind the scene to ensure the success of this training course. We are grateful to all of them that they have done good work. Dear participants, now for you, as you complete this course, I encourage you to take with you not only the knowledge you have gained, but also the spirit of curiosity and inquiry that brought you here in the first place. Continue to explore, question, and innovate. Interact with each other. Let your understanding of vacuum application open doors to new possibilities in your careers and research endeavors at your parents' departments. I wish each one of you success in your future endeavors, and I look forward to witness the remarkable contributions you will make in the field of vacuum applications and applied surface sciences. Thank you for your attention, and once again, congratulations on the accomplishment of this. Thank you very much, Pakistan Science.
Sir, for your inspiring words and insights to the importance of vacuum applications. Now I invite President Pakistan Vacuum Society, Dr. Javed Ahsan Bhatti, for the vote of thanks.
Bismillahirrahmanirrahim. In the name of Allah, most gracious, most merciful. Honorable Chief Guest, Mr. Muhammad Naeem, Shane Imtiaz, Halal Imtiaz, Satara Imtiaz, former Chairman, Pakistan Atomic Energy Commission. Honorable Guest of Honor, Professor Dr. Shahid Mahmood, Chairman, Pakistan Science Foundation. Guest of Honor and main resource person, Professor Dr. John T. Grant, Head of the Applied Surface Division, USTA, National Union. Honorable Patron, Pakistan Vacuum Society, Engineer Tahir Ikram. Chaudhry Tariq Sar, Coordinator of the International Technical Training Course. Distinguished guests, ladies and gentlemen, Assalamu alaikum and good afternoon. Just 2 days ago, in this good-looking hall, the International Technical Training Course on Vacuum Applications in Applied Surface Science was inaugurated. This event has now, by the grace of Allah, come to an end. I feel great
pleasure in welcoming all of you at this closing ceremony. I am extremely grateful to Engineer Muhammad Naeem Sahib, Tishan Imtiaz, Halal Imtiaz, Sar Imtiaz, who has very kindly agreed to be the chief guest at the closing ceremony. I am highly obliged to him for taking out a time for this event out of his very busy schedule. Dear participants, the objective of the International Technical Training Course was to enable scientists, engineers, and industrial people to assess the possible utility of vacuum technique applied on surfaces by their purposes, for their purposes. This technical activity gave better solutions to various surface-related processes that can be combined with each other to provide suitable solutions for their different problems. It suggested acceptable operating procedure and indicated mistakes that should be avoided during the operation of the vacuum system and vacuum plants. In addition, people from various parts of the country had an opportunity to sit together and discuss new trends in emerging technologies. In order to create awareness, understanding, and proper utilization of surface techniques in research and industrial organizations, the main focus was on surface characterization techniques and their analysis. This level of training course started from the basic knowledge to the latest practical application. The participants got opportunities to discuss their vacuum-related problems with experts of Pakistan Vacuum Society who are capable enough to find solutions to their technical problems. Ladies and gentlemen, this was the 9th international event organized by the Pakistan Vacuum Society, and it is heartening to note that this meeting was attended by a large group of technical people representing many research institutes and industries, and also from international participants. I reiterate our commitment that the Pakistan Vacuum Society will continue to provide the best possible services to the people related directly or indirectly to vacuum technology and its application in numerous advanced technologies. We look forward to suggestions in order to make it more effective. As a result of this interaction, we now have a better appreciation of the requirements of the business industry, such organizations, and educational institutes. Distinguished guests, knowledge has no limit, and this is true in all disciplines. No matter what you do or what you learn, strive for the other limits too. The more inquisitive you become, the better clarity of concepts you will achieve. And this is one of the factors that lead to success. This high-tech form of scientists and technologies would enable the countrymen to benefit from the latest developments in the field of the role of vacuum in applied surface sciences. May Allah shower His mercy and blessing on our scientists and engineers. This event provided the necessary confidence to our scientists to advance in frontiers of modern science and technology and lead the country towards the most secure and prosperous future. On behalf of PVS, Pakistan Vacuum Society, I must record my thanks to various departments for supplying the vacuum technology equipment for demonstration and for training purposes on loan basis for previous events. I am really grateful to Engineer Muhammad Naeem, former Chairman PAC, for accepting our invitation and gracing this event as a chief guest, and to Dr. Shahid Mahmood, Chairman, Pakistan Science Foundation. Dr. Shahid Mahmood, I am really very grateful to you for your kind comments for the Pakistan Vacuum Society, and I am to inform you that all the events of the Pakistan Vacuum Society are partially funded by the Pakistan Science Foundation.
It is the seed money of the Pakistan Science Foundation which keeps the activities of Pakistan Vacuum Society alive. Thank you, Dr. Shah Sahab. Thank you. I am highly thankful to Professor Dr. Iqbal Chaudhary, Coordinator General Comstech, for generously supporting this event. Without his support, this event would have not been possible. My special thanks go to Mr. Haris Akram and Mr. Hasib of Comstech, who have assisted us with whatever we need here at Comstech for arranging this event. I appreciate their dedication and hard work in this regard. I am really grateful to officers and staff of Comstech for managing this event in the best possible manner. All the credit of this successful event go to the patron of Pakistan Vacuum Society, Mr. Tahir Ikram, whose entire moral and material support has made this event to happen. I am thankful to Vista, Pakistan Foundation, Kunche, Sialkot, Al-Kartas, EPRF, International Vacuum, NASDAQ, People's Steel Mill, and other organizations who have supported us financially for managing this event. My special thanks and appreciation go to Chaudhary Tariq Sattar, coordinator of the course, and his team, whose visionary leadership, untiring efforts, and material support has made this event end with great success. I would like to express my personal gratitude to the organizing committee and support staff of Pakistan Vacuum Society, who took very keen interest in the affairs of society and made this event a success. Particularly, I appreciate Mr. Akhtar Amin, Mr. Yasin Shami, Dr. Yasin Shami, Mr. Muhammad Riyaz, Dr. Muhammad Arif and Rahid Iqbal, Mr. Fiazuddin, Dr. Allah Baksh, Mr. Bashar Hiyat, Dr. Rafiq, Mr. Osman, and his support staff. I am really grateful to them for their efforts making this event a success. In the end, I express my special thanks to all of you for coming here and joining this ceremony. Finally, on behalf of PBS, we offer our expert services concerning vacuum technology related your problems. You may consult our experts and discuss your problems whenever you need with the experts of Pakistan Vacuum Society. You have the email and mobile numbers. You can really discuss your problems and projects. Our experts are always available to you without any rewards. Before I close my talk, I taking the advantage of the presence of Dr. Grant here from UVista. Dr. Grant is very important personality and very important person in the International Union for Vacuum Science Technology and Applications. He is heading one of the division, very important division in the union. I request Dr. Grant, please award us one ECM, Executive Council meeting of International Union in Pakistan. We will offer our support here in Pakistan. Please help us in organizing this event. When these experts, the top experts of the Executive Council meeting of the International Union, if they agree, they come here in Pakistan, we will organize an international symposium on vacuum science and technology for 3 days. And the speakers will be all from the International Union. Dr. Grant, please help us. Thank you. And at the end, I am very much thankful to you, to the our worthy guest here. Whenever we organize Pakistan Vacuum Society event in the future, you please come and attend our events. Thank you very much.
Thank you very much, sir. As already mentioned by Dr. Javed, so this event was jointly organized by IUS, Pakistan Vacuum Society and Comstech. So at the end, I would request Mr. Hasib Ahmed from Comstech for his vote of thanks.
Assalamu alaikum, everyone. On behalf of Comstech, I would like to firstly thank all our distinguished guests present here for the closing ceremony. Excellencies, thank you for taking out your precious time to be here today. I would also like to appreciate our resource person, Professor John Grant, the participants and the exhibitors for making this event a success. A special thanks to our international participants, Dr. Noor, Dr. Atika from UITM, Dr. Fajr from University Erlangen, who are members of our Comstech Consortium of Excellence, and to Dr. Munawar, who have traveled from China. So thank you to all of you for coming and traveling to our beautiful country. Lastly, I would like to also thank the organizing committee for Pakistan Vacuum Society, the Comstech team, and the media who has covered this event for all their assistance throughout this event. Thank you so much, sir.
Thank you, Mr. Hasib Ahmed. Sir, in this workshop, in addition to the technical sessions, we also have a poster session. Posters were categorized in these areas like systems, coatings, and surface sciences. So in all three categories, 3 posters were selected by the committee. So I would like to announce the 3 best posters in all 3 categories. Number 1, Mr. Tahir from Ninvest. And the other poster, Mr. Rao from Ninvest and Ms. Aksa from IST. Sir, now we formally close the International Technical Training Course on Vacuum Applications. I request chief guest along with the worthy guests to come in front of the podium for the distribution of the sheets and the certificates. So we start with the prize of the posters. First, I call Mr. Tahir from Invest to receive his souvenir and the cash prize. Mr. Rao from Invest. Mr. Aksa from IST, maybe she is not here, and Dr. Vakil will collect the prize in place of Ms. Aksa. Now we will present the souvenirs and the certificates to our foreign participants. So first of all, I will request Dr. Noor Asnida from Malaysia to collect his certificate and the souvenir. Dr. Atika Kadri from Malaysia. Dr. Fajr Mulaya from Indonesia. And Dr. Munawar Iqbal from Pakistan. But this course was not possible without the resource persons. Now we will give the souvenirs to the resource person. I will be the last person. To Shahzad Alam. Dr. Vilayat Hussain. And finally, Professor Dr. John T. Grant. And now at the end, the teams of so now I will call the organizer of this workshop, Mr. Nasir Hussain, Mr. Yusuf Zia, Mr. Fiazuddin, Dr. Allah Baksh, Mr. Omar Usman, Mr. Ishfaq Ahmed, Mr. Akhtar Amin, Mr. Muhammad Riaz, Dr. Muhammad Rafiq, Dr. Wakil Khan, Mr. Mubashir Hayat, Dr. Yasin Shami, Mr. Hasib Ahmed, Mr. Haris Ikram, Mr. Haris Ikram, and Chaudhry Tariq Star. So now we will present the shields to our guest of honor. Now I will request Patron Chief to give the shield to the chief guest. And Dr. Chaudhary Tariq Star will give the shield to the Patron in Chief. So thank you very much, sir, for your presence and the patience. Now we have a refreshment in the adjacent hall. Thank you very much, sir.